The universe has a speed limit and it cannot be broken. Light moves through space at nearly 300,000 kilometers per second. Nothing we know can go faster than that. No rocket, no technology, and no theory can change this. But is there a law that controls how time works, how energy moves, and how the universe changes? Before we start, tell us in the comments below where in the world you're watching from and what time it is there now, so settle in as we explore why nothing can go faster than the speed of light. The speed of light is one of the most fascinating and mysterious constants in the entire universe. It travels at about 299,792 kilometers per second through the emptiness of space. This number may sound abstract, but its meaning is extraordinary. In just 1 second, light can move around the Earth more than 7 times. It moves so quickly that to the human eye, light seems instant. When we turn on a lamp, the room brightens immediately. When we look up at the night sky, we see stars that are light years away, and yet their light reaches us as a shimmering glow that seems to happen in the present moment. But in truth, we are seeing the past because light, even though unimaginably fast, still takes time to travel from one point in space to another. This astonishing speed, often written as the symbol c in physics, is not just a random number or a simple property of light. It is one of the most fundamental features of the universe itself. Scientists discovered that nothing, absolutely nothing, can travel faster than light in a vacuum. No spaceship, no signal, no particle, and no form of energy has ever been observed to break this boundary. It is not just a limit that technology cannot reach. It is a cosmic law that defines how space, time, and energy behave. To understand why light holds this special position, it helps to explore what light actually is. Light is a form of electromagnetic radiation, meaning it is both an electric and magnetic wave that moves through space. Unlike sound waves, which need air or water to travel, light does not need any medium at all. It can travel perfectly well through the emptiness of space, which is why sunlight reaches the Earth across about 150 million kilometers of vacuum. What makes light even more remarkable is that it always moves at the same speed, no matter who is observing it or how fast they are moving themselves. This strange fact puzzled scientists for centuries. Before the 20th century, most people believed that light must travel through some invisible substance, often called the ether. They imagined that this ether filled all of space, serving as a background through which light waves could move, much like sound waves move through air. But when scientists tried to detect this ether using careful experiments, they found nothing. The most famous of these tests was done in the year 1887 by Albert A. Michelson and Edward W. Morley. Their results showed that no matter how the Earth moved through space, the speed of light remained constant. There was no sign of any ether at all. This discovery set the stage for one of the greatest revolutions in physics. In the year 1905, a young patent clerk named Albert Einstein published his theory of special relativity. In it, he proposed something astonishing. The speed of light is not just constant. It is the same for everyone, everywhere, at all times. No matter how fast you move toward or away from a beam of light, you will always measure its speed as 299,792 kilometers per second. This single idea changed our entire understanding of the universe. Einstein realized that for the speed of light to remain constant, something else had to change instead. That something was space and time themselves. If light's speed could never vary, then distances and durations must stretch or shrink depending on how fast an object moves. This led to the astonishing conclusion that time is not absolute. It can slow down or speed up depending on your motion. Similarly, space can contract or expand. The faster you move, the more time slows for you, and the shorter distances appear in your direction of travel. All of this happens because the speed of light acts as the ultimate limit. It is as if the universe built a barrier that nothing with mass can cross. As an object moves faster and faster, it requires more and more energy to continue accelerating. For ordinary speeds, like cars or rockets, this extra energy is small enough to be manageable. But as something approaches the speed of light, the energy it needs grows dramatically. In fact, it grows toward infinity. That means that to reach the speed of light, you would need an infinite amount of energy, and infinity is simply not possible. This is why no object with mass can ever reach, let alone exceed, the speed of light. This natural limit is not a problem in physics, it is a foundation. Without it, the laws of the universe would not work the way they do. Light speed ties together energy, mass, and motion in a perfect mathematical relationship. This is the meaning behind Einstein's most famous equation, E mc2. It shows that energy, E, and mass, m, are two sides of the same coin, connected by the square of the speed of light, c2. Because c is such a huge number, even a small amount of mass holds an enormous amount of energy. That is why nuclear reactions, which convert tiny amounts of matter into energy, can release such incredible power. What makes the speed of light even more fascinating is that it defines how information moves. Nothing can carry a signal faster than light. If you send a message to someone on Mars, even if you use the most advanced technology possible, your message would still take several minutes to arrive because light takes that long to cross the distance. This delay is not due to any flaw in communication devices. It is a direct result of the cosmic speed limit. The same rule applies everywhere, from a simple radio signal to the most energetic cosmic rays. The limit also shapes how we experience time and reality. Because light takes time to travel, everything we see in the universe is a glimpse of the past. The light from the sun that warms our faces left the sun about 8 minutes ago. The light from the nearest star beyond our solar system took more than 4 years to reach us. The light from distant galaxies that astronomers observe through telescopes may have travelled for billions of years before finally arriving at Earth. In a sense, when we look into the night sky, we are looking through a cosmic time machine, seeing the universe not as it is now, but as it once was. Scientists consider the speed of light the ultimate limit because it connects deeply with the structure of spacetime itself. In Einstein's view, space and time are not separate things. They are woven together into a single four-dimensional fabric called spacetime. The speed of light defines how this fabric is stretched and curved. When massive objects like stars or black holes bend spacetime, light follows the curves. That is why gravity can bend light, an effect known as gravitational lensing. It was first observed during a solar eclipse in the year 1919, when astronomers noticed that starlight passing near the sun appeared slightly shifted. This confirmed Einstein's theory and proved that the speed of light interacts with the geometry of space and time. Even the fastest particles in nature, such as neutrinos or cosmic rays, cannot exceed this limit. In some experiments, scientists have measured particles coming close, incredibly close, but never beyond. Whenever it seemed like something broke the rule, further investigation always revealed errors or misunderstandings. The limit stands firm. What makes the idea even more astonishing is that the speed of light remains constant regardless of the source's motion. If a spaceship moves toward you at half the speed of light and it shines a beam of light, you might expect that the beam's speed would add up to 1.5 times the speed of light. But that never happens. The beam will still travel at the same 299,792 kilometers per second. To make this possible, time and space adjust themselves in such a way that everything fits perfectly. Because of this, the speed of a light is more than just a physical speed. It is a universal rule that defines what speed itself means. It is woven into the very equations that describe motion, energy, and causality. It even determines the order of events. For example, because no information can move faster than light, cause and effect always remain in the proper order. A cause must always happen before its effect. If it were possible to send signals faster than light, it could allow communication backward in time, breaking the chain of causality. The universe prevents this by fixing the cosmic speed limit. In the world of modern technology, the effects of this limit may seem subtle, but they are everywhere. Global positioning systems, GPS, rely on satellites that send light-speed signals to Earth. The calculations that determine your location must account for relativity, including time dilation due to both speed and gravity. Without these corrections, GPS would drift by several kilometers each day. This means Einstein's theory and the constancy of the speed of light are not just ideas for textbooks, they are practical necessities for modern life. Astronomers also depend on the speed of light to measure distances in the universe. Because they know how fast light travels, they can determine how far away stars and galaxies are based on how long their light has taken to reach us. When we say something is 1,000 light years away, we mean its light has been travelling for 1,000 years. This way of measuring space shows just how vast the cosmos truly is. Even our own galaxy, the Milky Way, is about 100,000 light-years across, meaning light takes 100,000 years to move from one side to the other. Light speed also defines the boundaries of what we can observe. The universe has a finite age, about 13.5 billion years, and since light can only travel so far in that time, we can only see as far as light has had time to reach us. This creates what astronomers call the observable universe. Beyond that, there may be endless galaxies and stars, but their light has not yet had enough time to arrive, so they remain invisible to us. The cosmic speed limit thus defines the edge of our cosmic horizon. Even though nothing can go faster than light, scientists continue to study what happens near that extreme. In particle accelerators, protons and electrons are pushed to speeds incredibly close to the speed of light. As they approach this limit, their mass appears to increase, requiring enormous energy to accelerate them even a tiny bit more. The closer they get, the harder it becomes, until the effort needed becomes infinite. This perfectly matches Einstein's predictions and proves again that the speed of light is absolute. Interestingly, not all forms of light travel through materials at the same speed they do in a vacuum. When light moves through air, water, or glass, it slows down slightly because it interacts with the atoms of the material. This slowing causes refraction, the bending of light that makes objects look distorted underwater or creates rainbows through prisms. But even in these cases, the ultimate limit, the vacuum speed of light, remains unchanged. It is the maximum possible speed, even though light may appear slower when moving through matter. Some scientists have explored whether there might be shortcuts around this limit, such as hypothetical wormholes or warp drives that could bend space itself to allow travel faster than light. According to Einstein's equations, such distortions of spacetime might be possible in theory, but they would require forms of energy or matter that we have never observed, such as negative energy or exotic matter. These ideas remain speculative and untested. The cosmic speed limit still stands unbroken. There have also been experiments that seem to challenge this rule. In 2011, a group of scientists in Europe reported that neutrinos might have travelled slightly faster than light. For a brief moment, it appeared that one of physics' most sacred laws might fall. But later investigations revealed that the apparent result was due to a loose cable in their measuring equipment. Once fixed, the results aligned perfectly with Einstein's predictions. This incident served as a reminder of how precise and reliable the law of light speed truly is. Another reason scientists consider the speed of light the ultimate limit is that it underlies the very structure of physical laws. The equations that describe electricity, magnetism, and gravity all depend on it. If the speed of light were different, even slightly, the universe would not look the same. Atoms might not hold together in the same way, stars might burn differently, and the forces that shape matter could collapse or explode unpredictably. The delicate balance that allows life, energy, and motion to exist depends on this single value. Because of this, some physicists call the speed of light a cosmic constant. It does not depend on where you are, how fast you move, or even when in history you measure it. It is part of the universe's very design, a number written into the code of existence. This constancy gives the universe its stability and predictability. It is the reason we can make calculations about the stars, launch spacecraft, and understand the past and future of the cosmos. The concept of light speed as a limit also helps scientists understand some of the strangest objects in the universe: black holes. A black hole's gravity is so strong that even light cannot escape once it crosses a certain point called the event horizon. This does not mean the black hole breaks the speed of light rule. Rather, it shows how powerful gravity can bend spacetime itself. At the event horizon, space and time are warped so extremely that all possible paths for light curve inward. Light cannot move outward faster than the spacetime around it pulls inward, so it becomes trapped. This is another way the speed of light defines the boundaries of physical reality. In the early universe, when everything was incredibly hot and dense, light played a crucial role in shaping how matter spread out. For the first few 100,000 years after the Big Bang, the universe was filled with a glowing fog of particles and radiation. Light kept bouncing off electrons, unable to travel freely. But as the universe expanded and cooled, light finally broke free and began its long journey through space. That ancient light still fills the universe today as the cosmic microwave background radiation, a faint glow that scientists can detect from every direction. Its existence and its properties confirm that light has always followed the same cosmic speed limit for more than 13 billion years. For more than 13 billion years. Even time itself seems tied to the speed of light. Because light defines how cause and effect spread through space, it also defines how we experience the flow of time. In physics, time can be thought of as the rate at which light moves through space. The closer you travel to the speed of light, the slower time passes for you relative to others. This is not science fiction. It has been proven in experiments with fast-moving particles and precise atomic clocks aboard satellites. The faster the motion, the slower the clock ticks. If it was somehow possible to travel at the speed of light, time would stop altogether for you. From your perspective, your journey would seem instant, no matter how far you travelled. But from the viewpoint of an observer standing still, your trip would take the normal amount of time according to the distance. This strange difference in experience is another result of the cosmic speed limit. It shows that time is not separate from motion. It is connected to it in every possible way. Light also plays a key role in defining the colours and patterns we see. The visible spectrum, which includes red, orange, yellow, green, blue and violet, represents different wavelengths of light, all travelling at the same speed. The difference in colour comes from how many waves pass each second, not how fast they move. This consistency ensures that light behaves predictably, whether it comes from a candle or a distant galaxy. In the broader sense, the speed of light connects everything that exists. It links the smallest particles with the largest cosmic structures. It shapes how stars shine, how galaxies evolve, and how the universe expands. Astronomers use it to measure cosmic distances, physicists use it to test theories of gravity and quantum mechanics, and engineers use it to design communication systems and technologies that depend on precise timing. It is the quiet ruler of motion, the invisible standard against which everything moves. Even in the most extreme places like neutron stars or quasars, where gravity and energy reach unimaginable levels, the rule remains the same. Light still travels at its fixed speed, no matter how strong the forces around it become. The entire universe, from the smallest atom to the largest galaxy cluster, operates under this same unbreakable limit. Long before people fully understood what light really was, they were already fascinated by how fast it moved. To ancient thinkers, light seemed instant. You lit a torch, and the room was bright immediately. You saw lightning before you heard thunder, but the flash itself appeared to happen at the very moment it was created. Because of this, for thousands of years, people thought that light had no speed at all, that it simply appeared everywhere at once. Yet behind this simple illusion was one of the greatest mysteries in nature. How fast does light really travel? The journey to discover the speed of light was long, filled with brilliant ideas, creative experiments, and plenty of mistakes. Some of the greatest minds in history, from Galileo Galilei in the early 17th century to old Römer in the late 17th century, and later James Clerk Maxwell in the 19th century, each played a part in changing the world's understanding of light. Their work turned what was once a question of curiosity into one of the most important discoveries in all of science. In the early 17th century, Galileo Galilei, the famous Italian scientist who challenged the old beliefs about the universe, was among the first people to seriously wonder whether light had a measurable speed. Galileo was a man who liked to question everything. He had already shown that the Earth moved around the Sun, not the other way around, and had used his telescope to explore the heavens. Yet even for someone as bold as Galileo, measuring the speed of light was not easy. The tools of his time were simple, and the distances he could work with were far too small compared to the enormous speed of light. Around the year 1638, Galileo tried an experiment that would become legendary. He and an assistant climbed to the tops of two hills separated by a known distance. Some records say it was about 1 mile, while others say it was less. Each man carried a lantern covered by a wooden shutter. The idea was simple. Galileo would open his lantern, and as soon as his assistant saw the light, he would open his own. Galileo would then measure how long it took for him to see the light from his assistant's lantern. The hope was that the delay would reveal the time it took light to travel between the two hills. It was a clever idea for its time, but Galileo quickly ran into a problem. No matter how carefully they tried, the light seemed to travel instantly. Galileo could not detect any delay between opening his lantern and seeing the return light from his assistant. The only delay he noticed came from human reaction time, the split second it took a person to notice the light and open their shutter. This was not the fault of Galileo's design, but rather a result of light's incredible speed. Over such a short distance, light's travel time was far too quick to measure with the simple instruments of the 17th century. Still, Galileo's experiment was not a failure. It showed something important, that if light had a speed, it must be extraordinarily fast, much faster than sound or any object known at the time. Galileo himself concluded that if light had a speed, it was extraordinarily great, far beyond human ability to measure directly. His curiosity, however, set a challenge for future scientists. If the speed of light could not be measured on Earth, perhaps it could be measured by looking at the heavens. Several decades later, another scientist named Ole Rømer took up that challenge. Born in Denmark in the year 1644, Rømer was an astronomer who worked at the Royal Observatory in Paris. Unlike Galileo, who tried to measure light on Earth, Rømer looked to the sky for clues. He studied the moons of Jupiter, the largest planet in the solar system which could be seen through telescopes. Jupiter's largest moons move around the planet in regular orbits, and one of them, Io, passes behind Jupiter at predictable times. These events, called eclipses, were like natural clocks in space. Rømer noticed something strange about Io's eclipses. When Earth was moving closer to Jupiter in its orbit around the Sun, Io's eclipses seemed to happen earlier than predicted. But when Earth was moving away from Jupiter, the eclipses appeared to happen later. This puzzled astronomers at first. Some thought the moons were speeding up or slowing down. But Rømer had a different idea. What if the delay had nothing to do with the moon itself, and everything to do with the speed of light? After careful observation, Rømer realized that when Earth was farther from Jupiter, the light from Io's eclipses had to travel a longer distance to reach us. Because light travels at a finite speed, that extra distance caused a delay. On the other hand, when Earth was closer, the distance was shorter, and the light reached us more quickly. By comparing the timing differences between these eclipses, Rømer was able to estimate how long it took light to cross the diameter of Earth's orbit. In the year 1676, Rømer presented his findings to the French Academy of Sciences. He suggested that light took about 22 minutes to travel across the diameter of Earth's orbit, a distance of roughly 300 million kilometers. From this, the speed of light could be estimated to be about 220,000 kilometers per second. Although this number was lower than the true value we know today, it was the first time anyone had successfully shown that light does not move instantly. Rømer's discovery was revolutionary. For the first time in history, there was direct evidence that light had a measurable speed. Many scientists at the time found it hard to believe because it went against centuries of assumption. Even Isaac Newton, who lived during the same era, still viewed light as something that behaved more like tiny particles than like a wave. But Rømer's work proved that light behaved in a measurable, predictable way, and that its movement through space could be timed. Over the next decades, other scientists refined Rømer's method. In 1729, the English astronomer James Bradley used the phenomenon of stellar aberration, a tiny shift in the apparent position of stars due to Earth's motion, to calculate a more accurate speed for light. His result was about 301,000 kilometers per second, much closer to the value we now accept. Rømer's initial insight had opened the door to one of the most important physical constants in the universe. While Galileo and Rømer had shown that light moved at a finite speed, they still did not fully understand what light actually was. Was it a stream of tiny particles, as Newton believed? Or was it a wave, like sound or water ripples, as others such as Christian Huygens argued? This question would not be fully answered until centuries later, when physics itself took a new direction. In the 19th century, the Scottish physicist James Clerk Maxwell entered the story. Born in the year 1831, Maxwell was one of the brightest minds of his age. He had a deep love for both mathematics and the natural world. From a young age, he was fascinated by the patterns found in nature, from the rings of Saturn to the colours of light. As he grew older, he began to study electricity and magnetism, two forces that at the time seemed separate but mysterious. Scientists knew that magnets could attract or repel each other, and that electric currents could create magnetic fields, but no one fully understood how the two were connected. Maxwell began to explore these relationships using mathematics. Between the years 1861 and 1865, he developed a set of equations that unified electricity and magnetism into a single theory, the theory of electromagnetism. These equations, now known as Maxwell's equations, showed that electric and magnetic fields are not independent but are deeply linked. A changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field. Together, they can travel through space as waves. Maxwell then asked himself a remarkable question. If electric and magnetic fields can form waves, how fast do those waves move? When he calculated their speed from the known constants of electricity and magnetism, he found something astonishing. The value came out to about 300,000 kilometers per second, exactly the known speed of light. This was no coincidence. Maxwell realized that light itself must be an electromagnetic wave, a self-propagating disturbance in the electric and magnetic fields that fills all of space. This discovery was one of the most profound moments in the history of science. It meant that light, electricity, and magnetism were not separate phenomena, but different expressions of the same fundamental force. Maxwell's theory not only explained how light moved, but also predicted the existence of other kinds of electromagnetic waves, such as radio waves, microwaves, and X-rays, all travelling at the same cosmic speed. What Galileo had tried to measure with lanterns, and what Römer had observed across the orbits of planets, Maxwell had finally explained through mathematics. His equations gave a deep reason for why light travels at the speed it does, because it is bound by the properties of space itself. The constants that describe electric and magnetic forces determine that speed, meaning that light's motion is not just fast but fundamental. It is built into the structure of the universe. Maxwell's work also inspired new generations of physicists. It laid the foundation for the field of modern physics, leading to discoveries that would come decades later. Albert Einstein, born in the year 1879, was deeply influenced by Maxwell's equations. Einstein would later show, through his theory of relativity, that the speed of light is not only constant but represents the maximum speed at which any information or matter can travel. But even Einstein's revolutionary work stood on the shoulders of those earlier giants: Galileo, who first dared to question whether light's motion could be measured; Römer, who proved that it was not infinite; and Maxwell, who uncovered its true nature. Looking back, it is astonishing how these early experiments, though separated by centuries, connect so beautifully. Galileo's lanterns were simple tools of human curiosity. Römer's telescopic observations extended that curiosity beyond Earth into the solar system. And Maxwell's mathematical vision reached even farther, uncovering the universal laws that bind light, electricity, and magnetism together. Each of these scientists, in his own time, worked with the tools and understanding available to him. None could see the full picture, but each added a crucial piece to the puzzle. In Galileo's era, people thought the heavens were perfect and unchanging, and that light was something divine, not measurable. Yet his experiment on those hills in Italy, even though it failed to give a number, was an early hint that nature's laws could be tested by human hands. Römer, working decades later, turned his eyes to Jupiter and its moons, using the sky as his laboratory. His clever reasoning transformed astronomy into a tool for physics. Maxwell, centuries later, used the power of equations to see deeper than any telescope ever could, revealing that light was not a substance or particle alone, but a vibration in the fabric of reality. These discoveries also changed the way people thought about time and space. Before Römer, astronomers believed that light reached us instantly, which meant that they thought they were seeing celestial events as they happened. Römer showed that we actually see the past, that even light takes time to travel. When you look at Jupiter, you see it as it was nearly 40 minutes ago. When you look at the Sun, you see it as it was about 8 minutes ago. And when you look at distant stars, you're seeing light that left them years, centuries, or even millions of years in the past. That realization changed everything. It meant that light was not only a source of illumination, but also a messenger of time. Through it, we could look back into history, not just human history, but cosmic history. The night sky became a kind of time machine, and Römer's simple observations made that possible. Galileo's early failure also taught scientists an important lesson about limits. It showed that not all natural phenomena could be understood with human senses alone. Some truths required new methods, new instruments, and new ways of thinking. His approach, to question, to test, and to measure, became the foundation of the scientific method. Maxwell's equations, written more than 200 years later, completed what Galileo had started. They revealed that the speed of light was not a mystery of human measurement, but a built-in property of the universe itself. In his equations, the speed of light emerges naturally from two constants: the electric permittivity and magnetic permeability of free space. These describe how electric and magnetic fields interact in a vacuum. From these two values, the speed of light can be calculated, showing that light's motion depends not on what it passes through, but on the very structure of empty space. That idea reshaped physics entirely. It led to the realization that space and time are deeply connected, that the speed of light acts as a cosmic link between them. Without Maxwell's insight, Einstein's relativity would never have been possible. The constant speed of light became the foundation upon which modern physics was built, influencing everything from quantum theory to cosmology. The story of how humanity came to understand the speed of light is a story of persistence, creativity, and imagination. Galileo, working with lanterns and hills, showed the courage to ask questions that seemed impossible to answer. Romer, using the motions of distant moons, transformed observation into calculation. Maxwell, armed with mathematics, uncovered the elegant truth that light is an electromagnetic wave moving through space at a fixed, universal speed. Their combined efforts changed not just how we see light, but how we see reality itself. Light became more than just illumination. It became a constant of the universe, a bridge between the physical and the mathematical, the human and the cosmic. From Galileo's hilltops to Romer's observatory to Maxwell's equations, the quest to understand the speed of light reveals a timeless truth about science, that each discovery, no matter how small, brings us one step closer to understanding the grand design of the universe. At the dawn of the 20th century, the world of physics was filled with questions that seemed impossible to answer. Scientists had come a long way in understanding motion, gravity, and energy since the time of Isaac Newton, whose laws had described how objects moved on Earth and in space. For more than 200 years, Newton's ideas seemed perfect and complete. His laws explained how planets orbited the sun, how apples fell to the ground, and how forces acted on every object in motion. But as scientists began to study light, electricity, and magnetism more closely, strange results started to appear. Results that did not fit neatly within Newton's framework. Something was missing, and it would take a young, unknown scientist named Albert Einstein to find the missing piece and completely reshape humanity's understanding of time, space, and motion. Albert Einstein was only 26 years old in the year 1905 when he published a paper titled On the Electrodynamics of Moving Bodies. This paper, which later became known as the Special Theory of Relativity, would become one of the most revolutionary scientific works in history. Einstein was working at the Swiss Patent Office in Bern at the time, analysing inventions during the day and thinking about the mysteries of the universe at night. He was not part of any university or laboratory, yet his mind was filled with deep questions that few dared to ask. The world saw light as a wave that travelled through an invisible substance called the ether, believed to fill all of space. Scientists thought that motion through this ether could be detected, but all attempts to find it had failed. The most famous of these attempts was the Michelson-Morley experiment of 1887, which tried to measure Earth's movement through the ether using beams of light. The experiment showed no difference in the speed of light, no matter the direction or motion of the observer. It was a puzzling result that went against everything scientists expected. Einstein looked at this problem differently. He asked himself what it would mean to ride alongside a beam of light. What would one see? Would the light stand still? Would its waves freeze in place? According to the laws of electromagnetism developed by James Clerk Maxwell in the 19th century, the speed of light should always be the same in empty space, about 300,000 kilometers per second. Yet Newton's classical physics said that if you moved toward a wave of light, you should measure it as moving faster, and if you moved away, it should seem slower. The two ideas could not both be true. Einstein decided that Maxwell's equations were correct, and that something far more profound must be reconsidered: our understanding of space and time themselves. Einstein proposed two simple but groundbreaking principles. The first was that the laws of physics are the same in all places, and for all observers who are moving at constant speeds relative to one another. This idea means that there is no special or preferred frame of reference in the universe. Motion is always relative. Whether someone is standing still on Earth or traveling inside a spacecraft moving at a steady speed, the laws of nature work exactly the same way. The second principle was even more shocking. The speed of light in a vacuum is always constant, no matter how fast an observer is moving or how fast the source of the light is moving. These two principles may sound simple, but their consequences were enormous. If the speed of light is always constant, then time and space cannot be absolute. They must change depending on the motion of the observer. In other words, two people moving at different speeds might not agree on how long an event takes, or how far apart 2 points are. This was a complete break from the classical idea that time ticks the same for everyone, and that space is a fixed stage where events take place. In Einstein's universe, time and space were woven together into a single fabric called Spacetime, and that fabric could stretch, shrink, or twist depending on motion. To understand what this means, imagine two observers, one standing on the ground, and the other travelling on a train moving very fast, close to the speed of light. The person on the train sends out a beam of light from the centre of the carriage toward two mirrors at the front and back of the train. To the person inside the train, the light moves equal distances in both directions, bouncing back at the same time, but to the person on the ground, watching from outside, things look different. Because the train is moving, the light travelling toward the back of the train has a shorter distance to cover, while the light going toward the front has a longer path. Yet both beams of light must move at the same speed, 300,000 kilometers per second. The only way both observers can be correct is if time itself runs differently for each of them. The observer on the train experiences time more slowly compared to the one on the ground. This strange but real effect is called time dilation. Time dilation is one of the most famous predictions of Einstein's special theory of relativity. It means that time is not universal. It depends on the speed at which someone is moving. The faster you move, the slower your clock runs compared to someone who is not moving as fast. This is not just a theoretical idea. It has been proven in many experiments. When scientists send atomic clocks aboard fast-moving jets or satellites, they find that these clocks tick more slowly than identical clocks left on Earth. The difference may be small, but it matches Einstein's equations perfectly. Even the Global Positioning System, or GPS, that helps navigate cars and airplanes today must account for this relativistic time difference. Without Einstein's corrections, GPS would quickly become inaccurate. Another equally fascinating effect predicted by special relativity is length contraction. Just as time slows down for an object moving close to the speed of light, distances also shrink in the direction of motion. If a spaceship were to travel near light speed, observers watching from Earth would see the ship become shorter, compressed along its direction of travel. However, the people inside the ship would not notice any change. To them, everything would feel normal. This shrinking of space is not an illusion. It is a real physical effect that arises because space and time are interconnected. What one observer calls a meter, another observer moving at a different speed might measure as shorter. Both time dilation and length contraction come from the same idea, the constancy of the speed of light. Light always travels at the same speed, no matter how fast you are moving. To preserve this rule, the universe must adjust time and space themselves. Einstein showed that time and space are not separate, independent entities, but are linked together into space-time. What one observer perceives as time, another might perceive partly as distance, depending on their relative motion. This deep connection between space and time is one of the most beautiful and mind-expanding concepts in all of science. But Einstein's theory did not stop there. It also revealed that as an object moves faster and faster, it gains more energy, and therefore its mass effectively increases. This means that the closer something gets to the speed of light, the harder it becomes to make it go even faster. At everyday speeds, this effect is too small to notice, but at speeds approaching that of light, it becomes enormous. A small particle in an accelerator, for example, requires greater and greater amounts of energy to accelerate as it approaches light speed. No matter how much energy is applied, it can never actually reach or exceed the speed of light. This is why Einstein's theory implies that the speed of light is not just very fast, it is the ultimate speed limit of the universe. Nothing that has mass can ever reach the speed of light because, according to Einstein's famous equation, energy and mass are two sides of the same coin. The equation says that energy equals mass times the speed of light squared. Since the speed of light squared is a huge number, Even a small amount of mass corresponds to an enormous amount of energy. This means that as an object's speed increases, its kinetic energy adds to its mass. To push it closer to the speed of light would require infinite energy, something the universe simply cannot provide. Therefore, light, which has no mass, can move at that ultimate speed, but anything with mass must remain slower. Einstein's equation also revealed a profound truth about matter and energy. They are interchangeable. Mass can be converted into energy, and energy can become mass. This idea was later confirmed in nuclear reactions, where small amounts of mass are transformed into vast amounts of energy, as seen in the Sun's fusion process and in nuclear power plants on Earth. The connection between mass and energy is one of the most important discoveries in the history of science, and it all came from Einstein's special theory of relativity. The theory also changed how scientists understood simultaneity, the idea that two events can happen at the same time. In everyday life, we assume that at the same time means the same for everyone, everywhere. But according to relativity, simultaneity depends on the observer's motion. Two flashes of lightning that appear simultaneous to a person standing still might not seem simultaneous to someone moving quickly in a train. For one observer, one flash may seem to happen before the other. This shows that time is not absolute but relative to motion. The order and timing of events can depend on how fast someone is moving, which was an idea that completely transformed philosophy as well as physics. Einstein's insights were not easy for people to accept at first. The idea that time could slow down or that distances could shrink went against all common sense. Yet experiment after experiment confirmed his predictions. In the mid-20th century, scientists studied fast-moving particles called muons, which are produced by cosmic rays striking Earth's atmosphere. These particles decay very quickly, usually within microseconds. However, when they move close to the speed of light, their internal clocks slow down due to time dilation, allowing them to travel much farther before decaying. This observation perfectly matched Einstein's theory and provided powerful evidence for relativity. Another experimental proof came from studying atomic clocks flown around the Earth in airplanes. These clocks showed a tiny but measurable difference compared to clocks on the ground, exactly as relativity predicted. Modern particle accelerators, such as those used in the early 21st century at CERN in Switzerland, also confirm that particles gain mass and energy according to Einstein's equations. Every experiment, from the smallest subatomic particle to the vast behavior of stars, agrees with the special theory of relativity. Einstein's work also opened new paths for understanding the universe on a grand scale. The special theory of relativity dealt only with objects moving at constant speeds in straight lines. It did not include gravity or acceleration. But Einstein realized that if motion affects time and space, then gravity must as well. This realization led him, 10 years later, in the year 1915, to develop the general theory of relativity, which described gravity not as a force but as the curvature of spacetime caused by mass and energy. Without the special theory of relativity, that later breakthrough would never have been possible. The special theory of relativity also changed how we think about light and energy. Light, according to the theory, behaves both as a wave and as particles called photons, which always travel at the same constant speed in a vacuum. Because nothing can go faster than light, the speed of light becomes a fundamental boundary for all motion and information in the universe. It sets the limit for how fast cause and effect can travel. If something could move faster than light, it would break the logical order of events. It could, in theory, allow effects to happen before their causes. This would destroy the very structure of time itself, something nature does not allow. This universal speed limit has profound implications for space travel and communication. Even if humans one day build spacecraft that can approach a significant fraction of light speed, they would still face enormous challenges. The energy required to accelerate a ship to near light speed would be astronomical, and time would pass differently for those aboard compared to people on Earth. For example, if astronauts traveled to a distant star at 99.9% the speed of light, they might experience only a few years during the journey, while decades or even centuries could pass on Earth. This is not science fiction. It is a real effect predicted by Einstein's equations and supported by experimental evidence. The special theory of relativity also reshaped philosophy, art, and literature, inspiring new ways of thinking about time, perception, and the human experience. Before Einstein, time was seen as a steady, universal flow that moved the same for everyone. After Einstein, time became flexible, personal, and deeply connected to motion. This realization changed how people thought about existence itself. Artists began to explore new ways of representing motion and perspective. Writers started to play with non-linear storytelling, reflecting the relativity of time. Philosophers discussed the meaning of reality in a universe where time and space depend on the observer. Einstein's theory did not just remain in books, it became part of the very fabric of modern life. Technologies like particle accelerators, nuclear power, and even everyday electronics depend on principles derived from relativity. The synchronization of satellites that form the backbone of global navigation systems relies on relativistic corrections to maintain precision. If engineers ignored these effects, GPS coordinates would drift by several kilometers every day. Even digital communication and advanced medical imaging technologies are influenced by the physics that Einstein uncovered. The beauty of the special theory of relativity lies not only in its scientific accuracy, but also in its simplicity. Einstein built it from just two postulates, two clear ideas about the constancy of physical laws and the unchanging speed of light. From those ideas came a completely new vision of the universe. The equations that emerged from his theory showed how time, distance, mass, and energy transform as objects move at high speeds. For example, the famous Lorentz transformation equations describe how coordinates and time change between two observers in relative motion. They replace the simple addition of velocities used in Newtonian mechanics with a more accurate formula that keeps the speed of light constant for all observers. The deeper one looks into relativity, the more extraordinary it becomes. The universe, according to Einstein, is not a rigid stage but a dynamic fabric, shaped by motion and energy. Every movement, every flash of light, and every flow of time is part of this grand structure. Even though we experience time and space as separate things in daily life, relativity shows they are deeply intertwined. The ticking of a clock depends on motion, and the measurement of a distance depends on speed. The faster you move, the more the universe bends around you to keep the speed of light the same. The effects of relativity become truly noticeable only at very high speeds, close to that of light. For cars, planes, or even rockets moving at thousands of kilometers per hour, the differences are far too small to detect without precise instruments. But for particles in accelerators or objects traveling across cosmic distances, relativity governs every detail. Astronomers use Einstein's equations to calculate how light from distant stars and galaxies shifts in color as they move relative to Earth. This effect, called the Doppler shift or redshift, helps measure the expansion of the universe. The special theory of relativity also helps explain phenomena like the twin paradox, a thought experiment that highlights the strange effects of time dilation. In this scenario, one twin stays on Earth while the other travels through space at nearly the speed of light and then returns. Because of time dilation, the travelling twin would have aged less than the one who stayed on Earth. This idea, once seen as pure imagination, has been confirmed in experiments with fast-moving particles and precise clocks. It shows that time truly behaves differently for moving observers, a direct result of the relativity of time and space. Einstein's insights also brought forth a new understanding of symmetry in the laws of nature. His theory revealed that the universe does not prefer one state of motion over another. Whether someone is standing still or moving steadily, the rules remain identical. This elegant symmetry became a cornerstone of modern physics and inspired later theories that describe the fundamental forces of the universe. Before Einstein, physicists believed in an invisible ether that carried light waves through space. After Einstein, they no longer needed it. Space itself became the medium through which light traveled, self-contained and independent of any background substance. This simplification removed unnecessary assumptions and made physics more elegant and consistent. It also unified ideas about energy, motion, and electromagnetism that had puzzled scientists for decades. Over the years, countless experiments have continued to confirm Einstein's predictions. High-speed particle studies, satellite observations, and precise measurements of atomic time all match the equations of relativity with remarkable accuracy. Even after more than a century, no experiment has contradicted the principles Einstein set forth in 1905. The theory has stood as one of the greatest achievements of human thought, a revolution that changed how we understand reality itself. Einstein's special theory of relativity transformed the world of science, technology, and philosophy by revealing that time and space are not fixed but flexible, and that the speed of light is the ultimate cosmic limit. Through its principles, humanity discovered that the universe is not what it seems. It is a vast, dynamic realm where motion, energy, and existence are deeply connected in ways once thought impossible. The universe follows certain rules that never seem to break, no matter how strange or powerful the things in it become. One of those rules is the deep connection between energy and mass, a relationship that Albert Einstein made famous with his simple, yet revolutionary equation, E mc2. Behind those few symbols lies one of the greatest discoveries in all of science, that mass and energy are not separate things, but two different forms of the same underlying reality. This idea changed everything we thought we knew about how the universe works, from the smallest atoms to the largest stars, and it continues to shape how we understand speed, motion, and the energy that powers every process in existence. Before Einstein's time, scientists thought of mass and energy as two completely different concepts. Mass was something solid, something that made up physical matter, like rocks, planets, and people. Energy, on the other hand, was something invisible, something that made things happen, like heat, light, and motion. They were treated as separate ingredients of the physical world. But in the early years of the 20th century, Einstein showed that these two were not opposites or unrelated properties, but two sides of the same coin. Every bit of mass contains an enormous amount of energy, and every bit of energy has an equivalent mass. Einstein's discovery started with his famous special theory of relativity, published in the year 1905. One of the main ideas of this theory is that the speed of a light in a vacuum, about 300,000 kilometers per second, is the same for all observers, no matter how fast they are moving. This single idea forced scientists to completely rethink the nature of time, space, and motion. It also revealed that as an object moves faster and faster, its energy increases in a way that directly ties to its mass. To understand this relationship, it helps to think about how energy behaves when something starts moving. In everyday life, if you push a ball, you give it energy. The harder you push, the faster it goes. The energy you give it is called kinetic energy, the energy of motion. If you double the speed of the ball, you don't just double the energy, you actually quadruple it. That's because kinetic energy depends on both the mass of the object and the square of its speed. This relationship is already familiar in classical physics, long before Einstein came along. But what Einstein showed is that this pattern doesn't stop at ordinary speeds. It continues all the way up to the speed of light, and as an object gets faster, its total energy begins to rise in a way that changes how its mass behaves. In the world of relativity, as an object approaches the speed of light, something extraordinary happens. The faster it moves, the more energy it needs to keep accelerating. This energy doesn't just make the object move faster, it also adds to its mass. In other words, the object becomes heavier, not because it gains physical material, but because energy itself has mass. The increase is tiny when you move at everyday speeds, like a car on the road or a plane in the sky, but as the object moves faster and faster, nearing the cosmic speed limit, the energy requirement skyrockets. Let's say you have a spaceship and you want to make it go faster and faster. At first, you can add fuel and accelerate it without much trouble, but as you push it closer to the speed of light, the energy you need increases dramatically. At half the speed of light, the ship's energy requirement is already far greater than what any normal engine could provide. As it nears 90% of the speed of light, the energy needed to make it just a little bit faster becomes unbelievably huge. And as it approaches the full speed of light itself, the energy required becomes infinite. That means it is physically impossible to reach or surpass the speed of light if you have mass. The universe simply forbids it. This is one of the most important consequences of the relationship between energy and mass. It tells us that nothing with mass can ever reach the speed of light, because as it gets closer to that speed, it would require an infinite amount of energy to continue accelerating. Only light, which has no rest mass, can travel at that speed naturally. Everything else, no matter how powerful or advanced, must stay below that cosmic limit. The reason for this lies in Einstein's formula. The equation E mc2 means that mass can be turned into energy, and energy can be turned into mass. The c2, the speed of light squared, acts as a conversion factor between the two. Since the speed of light is such an enormous number, the square of it is unimaginably large. This means that even a tiny bit of mass contains an enormous amount of energy. That's why nuclear reactions, which convert small amounts of matter into energy, release so much power. In atomic bombs and nuclear reactors, a small fraction of the atom's mass is transformed into vast quantities of energy, proving Einstein's idea in the most dramatic way possible. But the relationship works both ways. Just as mass can turn into energy, energy can also turn into mass. When high-energy particles collide, the energy from the impact can create new particles, actual matter, out of pure energy. This process happens constantly inside particle accelerators and in the hearts of stars, where intense heat and pressure turn energy into new atoms. It also happened during the birth of the universe itself, when the enormous energy of the Big Bang cooled and condensed into the first particles of matter. The deeper we explore the relationship between energy and mass, the more we realize how perfectly balanced the universe is. Every particle that exists is like a frozen form of energy, a bit of the universe's total energy locked into the structure of matter. When that energy is released, it doesn't disappear, it just changes form. That's why Einstein's equation isn't just about physics, it's about the unity of everything. It shows that matter and energy are two expressions of the same cosmic substance, transforming endlessly from one form to another. When it comes to speed, this relationship becomes even more fascinating. Imagine trying to accelerate a particle, say an electron, inside a particle accelerator. The more energy you give it, the faster it moves. But as it gets closer to the speed of light, something strange happens. Instead of its speed increasing in the usual way, most of the added energy goes into increasing its relativistic mass, which is the mass it appears to have when moving near light speed. Its motion gets harder and harder to change. The particle moves faster, yes, but each small increase in speed demands far more energy than the last. By the time it's moving at 99.99% of the speed of light, the energy needed to make it just a tiny bit faster would be enormous, enough to power entire cities. That is why even the most powerful accelerators on Earth, such as those used in high-energy physics laboratories, can only make particles move very close to the speed of light but never reach it. Scientists have pushed particles to speeds where they move just a fraction of a percent below the speed of light, but never beyond. The closer they get, the heavier they become, and the more energy it takes to keep pushing them. This principle also explains why travelling across the universe at near-light speed would be so difficult for any spacecraft. As the ship's speed increases, its kinetic energy rises dramatically, and so does its effective mass. The engines would have to work harder and harder, and the fuel needed would grow beyond any reasonable amount. Even if we could somehow harness all the energy of a star, it would still not be enough to push a ship with mass to the full speed of light. That's why scientists explore other ideas, such as using light sails or theoretical warp drives. But even those depend on bending space itself rather than breaking the universal speed limit. The beauty of Einstein's discovery is that it unites the behavior of everything in motion. At low speeds, Newton's laws describe how energy and motion behave, and they work well enough for everyday situations like cars, airplanes, and falling objects. But as speeds increase and approach that of light, Newton's equations no longer work. They fail to explain the strange effects that begin to appear. Time slows down for the moving object, distances contract, and its mass increases. Einstein's equations, however, handle all of this naturally. They show that time, space, mass, and energy are all connected in a single fabric of reality that changes shape depending on how fast you move through it. This connection between energy and mass also reveals why the universe is so stable yet so dynamic. It explains how stars shine, how nuclear reactions power both the smallest atoms and the largest galaxies, and even how the universe itself evolves. Inside a star, hydrogen atoms fuse together to form helium, releasing energy in the process. This energy comes from the small difference in mass between the starting hydrogen atoms and the resulting helium atom. That lost mass becomes pure energy, radiating out as the light and heat that reach Earth from the Sun. Every second, the Sun converts about 4 million tons of matter into energy, proving Einstein's idea again and again across the vastness of space. This same process happens in nuclear power plants on Earth, though on a much smaller scale. Inside reactors, uranium or plutonium atoms are split in a process called fission, and part of their mass is released as energy. The fact that we can build machines that directly use this principle shows just how powerful and accurate Einstein's relationship between mass and energy truly is. It's not just a theoretical idea, it's a reality that powers our civilization and illuminates our skies. In the world of particle physics, this relationship goes even deeper. Every time scientists study collisions between particles in accelerators, they are watching the conversion between energy and mass in real time. When two protons collide at near-light speeds, the energy from their motion can briefly create entirely new particles, which then decay into others. This shows that mass and energy are interchangeable, that the universe constantly transforms itself through these exchanges. Even cosmic events follow this rule. When two black holes collide, for instance, a portion of their combined mass is converted into energy in the form of gravitational waves, ripples in spacetime that travel across the universe at the speed of light. These waves carry away immense amounts of energy, equivalent to several suns, showing again that mass and energy are part of one continuous process. Einstein's insight also helps explain why the early universe looked the way it did. Right after the Big Bang, everything that existed was pure energy. As the universe expanded and cooled, that energy began to turn into particles of matter and antimatter. Some of those particles annihilated each other, turning back into energy, while a small excess of matter remained. The atoms that would later form stars, planets, and eventually life itself. In that sense, everything that exists today, every atom in your body, every rock and planet, every drop of water, was once pure energy, transformed through the universe's natural processes. The relationship between energy and mass also shows up in small but measurable ways even in our daily lives. When you heat an object, you add energy to it, and because energy has mass, its total mass actually increases, even if only by an amount too tiny to measure with ordinary scales. The difference is incredibly small, but it is real. That's how deeply connected these two concepts are. If we return to the question of speed, the link between energy and mass reveals one of nature's most fascinating truths. The faster something moves, the more energy it contains, and the more it behaves as if it has greater mass. This is why accelerating to higher speeds requires exponentially more energy. It's not simply a matter of pushing harder, it's a fundamental change in how the object interacts with space and time. The energy doesn't just make the object move, it reshapes the very structure of its motion through space-time. In the late 20th and early 21st centuries, experiments have confirmed this again and again. Particle accelerators such as the Large Hadron Collider in Europe have shown that as particles are pushed to higher and higher speeds, their behavior matches Einstein's predictions perfectly. Their masses increase exactly as relativity describes, and their energies follow the relationship defined by E, mc2. No experiment has ever contradicted this. This relationship also provides an important clue about the future of energy itself. Because even a small amount of mass can produce enormous energy, scientists have long dreamed of finding safe and sustainable ways to release that energy, not through destructive explosions, but through controlled reactions. Nuclear fusion, for instance, aims to reproduce the process that powers the stars by merging light atoms to release vast amounts of energy from tiny amounts of matter. It's one of the greatest scientific goals of our time, and a direct application of Einstein's insight. On a deeper philosophical level, the relationship between energy and mass changes how we think about existence itself. It means that everything we see, touch, and experience is just a particular form of energy, temporarily arranged into what we call matter. Even the solid ground beneath our feet is, at its core, a kind of condensed energy field. The universe is not made of separate things, but of continuous energy patterns that take different forms. As we explore farther into the cosmos and study the behavior of stars, galaxies, and particles, the same truth keeps appearing. Energy and mass are inseparable. In the dance of creation and destruction that fills the universe, from the birth of stars to the collisions of galaxies, the same rule applies. Matter turns into energy, energy becomes matter, and through that constant exchange, the universe continues to evolve. Einstein's discovery also influences modern technology in ways we rarely think about. Devices that rely on nuclear energy, medical scanners that use positrons, and even the understanding of how GPS satellites correct for time dilation, all trace back to the same relationship. Without Einstein's understanding of how energy and mass interact, our modern world would look very different. If we think of the universe as a great balance, Energy and mass are what keep it in harmony. When something gains energy, it gains mass. When something loses energy, it loses mass. It's an ongoing exchange that maintains the total balance of the cosmos. The universe does not waste or destroy energy, it merely changes its form. In practical terms, this means that as we study motion, we are really studying the flow of energy and mass together. When a rocket launches, it burns fuel to release energy, which pushes it upward and increases its speed. But as the rocket accelerates, its energy increases and its mass effectively rises, requiring more fuel to continue accelerating. This is the same rule, just on a smaller and slower scale. So every time we talk about speed and energy, we are really talking about the same thing that Einstein discovered more than a century ago. Speed is the expression of energy in motion, and energy itself carries mass. The faster we move, the more tightly linked these two become, until we reach a point where they cannot be separated. The relationship between energy and mass is one of the most profound truths ever uncovered. It connects everything: motion, speed, heat, light, matter, and even time itself, into one simple yet powerful idea. It shows that the universe is built on unity, not separation, and that every form of existence is simply a transformation of the same fundamental essence. The closer we look, the more we see that this relationship governs every part of reality. From the motion of atoms to the life of stars, from the smallest particles in accelerators to the largest galaxies in space, energy and mass work together as partners in the eternal dance of creation, motion, and transformation. Nothing stands apart from this connection. It shapes the way things move, how fast they can go, and how much energy they hold. It is the foundation of every physical process and the reason why the universe behaves the way it does, endlessly changing yet perfectly balanced, bound forever by the link between energy and mass. Time is something we all experience every single day. We wake up, eat, work, and sleep according to it. We use clocks to measure it and calendars to organize it. We feel it moving forward at a steady pace, second after second, minute after minute, hour after hour. Yet, in the strange world revealed by modern physics, time does not always behave in the simple, predictable way we think it does. It can stretch, it can bend, and under certain conditions, it can even slow down. This remarkable and counterintuitive effect is known as time dilation. It is one of the most fascinating consequences of Albert Einstein's theory of relativity, a theory that forever changed our understanding of how the universe works. The story of time dilation begins with Einstein's special theory of relativity, which he published in the year 1905. Before Einstein, most scientists believed that time was absolute, that it flowed at the same rate for everyone, everywhere, no matter what. This idea made sense in everyday life. Whether someone was walking, riding a train, or sailing on a ship, it seemed that time passed equally for all. But Einstein showed that the universe does not follow that simple rule. Instead, he proposed that time and space are deeply connected, forming a single fabric called spacetime. The faster an object moves through space, the more its experience of time changes compared to something that is not moving as fast. In other words, the passage of time depends on motion. The faster something moves, especially as it approaches the speed of light, the slower its time flows compared to that of an observer who's not moving so quickly. This effect is not something we can normally feel in our daily lives because we move much too slowly compared to the speed of light, which is roughly 300,000 kilometers per second. But for objects moving near that extraordinary speed, time dilation becomes a powerful and measurable effect. To understand what this really means, imagine two people. Let's call them Sam and Lila. Sam stays on Earth while Lila travels into space aboard a spaceship that can move at a speed close to that of light. From Sam's point of view on Earth, Lila's clock on the spaceship ticks more slowly than his. Every second that passes for Sam might take a little longer for Lila. If she spends what seems to her like just a few years travelling at near light speed and then returns to Earth, she might discover that many more years have passed for Sam. She would be younger than her twin brother, even though they were born at the same time. This thought experiment, often called the twin paradox, is one of the most famous ways to show how time dilation works. Although this may sound like science fiction, it is a real effect supported by countless experiments. scientists have confirmed time dilation many times using precise clocks and high-speed particles. For example, atomic clocks placed on fast-moving airplanes or satellites tick more slowly than identical clocks on the ground. This difference is incredibly small, but it can be measured. In fact, without accounting for time dilation, the Global Positioning System, or GPS, which helps us find directions using satellites, would not work accurately. The satellites orbit Earth at high speeds, and their clocks experience time slightly differently from clocks on the ground. Engineers must correct for this difference so that GPS can give us accurate positions. One of the earliest experimental proofs of time dilation came from studying tiny particles called muons. Muons are created when cosmic rays from outer space strike the upper layers of Earth's atmosphere. These particles move incredibly fast, close to the speed of light, and they decay or disappear very quickly. When scientists first measured how long muons last, they expected to find that only a few would survive long enough to reach the surface of the Earth, because muons typically live for only a few millionths of a second. But when researchers actually counted them, they found many more than expected. The reason was that time for the muons was moving more slowly due to their immense speed. From our point of view on Earth, their internal clocks were ticking slower, allowing them to exist longer before decaying. This was a clear and direct demonstration of time dilation in action. The deeper one looks into Einstein's theory, the more fascinating it becomes. Time dilation is not merely a quirk of mathematics or a trick of perspective, it is a fundamental feature of the universe. The closer something moves to the speed of light, the more dramatically time slows down for it relative to an observer at rest. If we could somehow travel at 99% of the speed of light, time for us would move about 7 times slower than for people who remain on Earth. At 99.9% of the speed of light, time would move more than 20 times slower. At 99.999%, it would slow by a factor of hundreds or even thousands. In theory, if one could ever reach the exact speed of light, time would stop completely for that traveller. However, no object with mass can ever reach that speed because it would require infinite energy. This slowing of time also has strange consequences for the way we view the universe. To a traveller moving close to light speed, distances appear shorter and events seem to unfold differently compared to someone who is not moving as fast. This is because time and space are intertwined. As time slows down, space itself seems to contract in the direction of motion. So, while an astronaut speeding through space might feel as though their journey only took a few years, observers back on Earth might measure that trip as taking many decades or even centuries. This is why, in theory, time dilation could allow for something like time travel to the future. It does not involve jumping between timelines or using a machine. It happens naturally as a result of high-speed motion. Scientists and engineers must deal with the consequences of time dilation whenever they study high-speed motion or design technologies that rely on precise timing. For instance, the clocks aboard satellites used for communication or navigation must be carefully adjusted to account for both the effects of speed and gravity, which also influences time. Even though these satellites move much slower than the speed of light, the difference still adds up over time and can cause serious errors if not corrected. Time dilation also plays a key role in understanding what happens near black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape from them. According to Einstein's later general theory of relativity, gravity itself can warp spacetime, and this warping affects the flow of time. Near a black hole, time moves slower relative to places where gravity is weaker. So if someone could hover near the edge of a black hole for what felt like a few hours to them, years or even centuries might pass elsewhere in the universe. This gravitational time dilation is similar in spirit to the time dilation caused by motion, because both result from the same deeper principle. That time is not absolute but depends on how one moves through space-time. To see how dramatic this effect can be, imagine an astronaut orbiting near a black hole while another remains far away. The one near the black hole would experience time passing much more slowly. If they eventually escaped and rejoined their companion, they might find that their friend had aged far more than they had. In some extreme cases, the difference could be so large that the astronaut near the black hole would come back to find that thousands or even millions of years had passed in the outside universe. Einstein's equations predict all of this with remarkable accuracy, and experiments continue to confirm them. For instance, Scientists at laboratories such as CERN have accelerated subatomic particles to speeds extremely close to that of light, and they have seen their internal processes slow down exactly as predicted. These experiments show that time dilation is not just a strange theory, it is a real and measurable phenomenon. To make sense of why time behaves this way, we can think about how light works. In Einstein's theory, the speed of a light is always the same for all observers, no matter how fast they are moving. This rule forces time and space to adjust in such a way that the total speed of light never changes. If one person is moving quickly toward a beam of light and another is standing still, they will both measure the light moving at the same speed. To make this possible, time itself must slow down for the moving person. This keeps the laws of physics consistent for everyone, regardless of their motion. This is very different from how we think about speed in everyday life. If someone on a moving train throws a ball forward, and another person standing on the ground measures the ball's speed, they would add the speed of the train and the speed of the throw. But light doesn't behave that way. No matter how fast you move toward it or away from it, its speed remains constant. That unchanging speed is what causes all the strange effects of relativity, including time dilation. For small speeds, such as cars, planes, or even rockets, time dilation is so tiny that it makes no noticeable difference. But as one gets closer to the speed of light, it becomes impossible to ignore. Suppose a spaceship travels to a distant star located 10 light-years away. That means light takes 10 years to reach it from Earth. If the ship could move at 99.99% of the speed of light, people on Earth would see the trip taking more than 10 years. But for those aboard the ship, time would have slowed down so much that the journey might only feel like a few months. This strange difference shows that time is not universal. It depends on how one moves through space-time. If such a journey were ever possible, it would open up extraordinary possibilities. Astronauts could leave Earth, travel at near-light speed, and return centuries later while they themselves had aged only a few years. To them, it would feel as though only a short time had passed, but the Earth they returned to might have changed beyond recognition. Civilizations might have risen and fallen, continents might have shifted, and history would have moved far beyond their original era. Physicists often describe time dilation using a mathematical expression derived from Einstein's equations. It shows that as an object's speed increases, the passage of time decreases according to a precise formula. This relationship has been tested so thoroughly that it stands as one of the most accurate predictions in all of science. In fact, it forms the foundation for technologies that depend on high-speed precision, from particle accelerators to satellite communications. The phenomenon of time dilation also teaches us something profound about reality. It shows that time is not a single universal flow, but part of a flexible, interconnected fabric that includes space itself. What we experience as now is not the same for everyone, and what seems like a second to one person can be longer or shorter to someone else moving at a different speed or under a different gravitational influence. It suggests that our sense of time is deeply tied to our perspective, and that the universe's true nature is far stranger than our everyday experience allows us to see. Even though time dilation may sound strange, we see its effects all around us in the universe. The light from distant stars and galaxies often shows signs of time dilation because of how fast these objects move relative to us. In the early universe, when galaxies were much closer together and moving rapidly apart, their light stretched and slowed, carrying with it a record of the time differences that existed billions of years ago. Astronomers use this information to understand the age, structure, and expansion of the cosmos. Another fascinating example comes from pulsars, rapidly spinning neutron stars that emit beams of radiation. When these pulsars move at high speeds or orbit near other massive objects, their regular pulses appear to slow down because of time dilation. By carefully measuring these small changes, scientists can study gravity, motion, and even test aspects of relativity in extreme environments. Time dilation also raises deep philosophical questions. If time can slow down depending on how we move or where we are, what does that say about the nature of past, present, and future? Are they fixed and unchangeable, or are they simply different perspectives of the same underlying reality? Einstein himself once said that the distinction between past, present, and future is only a stubbornly persistent illusion. To him, time was part of a larger four-dimensional structure where all events, those we call past, those we experience as present, and those yet to come, exist together in a vast cosmic framework. For human beings, it is difficult to think in such abstract terms. We live our lives bound to the flow of time, always moving forward. But the concept of time dilation shows that this flow is not the same everywhere in the universe. In a sense, each of us carries our own personal clock, and that clock can tick at a different rate depending on how we move through space, or how strong the gravity around us is. Scientists continue to study time dilation, not only because it challenges our intuition, but also because it is essential to modern physics. Without understanding it, we could not make sense of the behavior of particles at high speeds, the functioning of satellites, or the way the universe expands. Each new experiment that confirms Einstein's predictions strengthens our understanding of the strange but beautiful relationship between time, space, and motion. In laboratories around the world, researchers have used increasingly precise instruments to test how time behaves under different conditions. In some experiments, scientists have cooled atoms to near absolute zero and measured how their internal vibrations slow down when they move at high speeds. In others, they have sent ultra-accurate atomic clocks aboard fast-moving aircraft or into space to observe tiny but real differences in time. Every time, the results agree perfectly with Einstein's theory. If we look far into the future, time dilation could become more than just a subject for study. It could become part of human experience. If one day we build spacecraft that can travel at a significant fraction of the speed of light, astronauts may truly experience time differently from those who remain on Earth. Their journey could serve as a direct window into the relativistic nature of the universe. What they experience as a few years of travel might correspond to hundreds or even thousands of years passing back home. In this way, time dilation transforms from a theoretical idea into something deeply human, reminding us that time itself is not an absolute ruler, measuring all events the same way, but a living, changing quality of the cosmos. It tells us that the universe is not just a stage where events unfold one after another. It is a dynamic web where time and space flow and twist together in intricate ways. The more scientists study time dilation, the more they realize how much it affects our understanding of everything, from the birth of the universe to the smallest particles of matter. It plays a key role in understanding how energy and mass interact, how stars live and die, and how the universe will evolve in the distant future. It shows us that nothing in nature is isolated, that motion, gravity, space, and time are all part of a single, magnificent structure, woven together by the laws of relativity. In our everyday lives, we may not feel the effects of time dilation, but they are there, quietly influencing the world around us. The satellites guiding our phones, the particles racing through the atmosphere, the stars shining in the night sky, all are affected by this subtle slowing and stretching of time. It is one of the universe's quiet wonders, a reminder that beneath the surface of ordinary experience lies a reality more complex and astonishing than we can easily imagine. Einstein's discovery of time dilation in the early years of the 20th century remains one of the greatest intellectual achievements in human history. It changed not only physics, but also philosophy and our perception of existence itself. It showed that time is not merely a background for events, but an active player in the cosmic story. It bends, it flows, it adapts, and it connects every object and every being in the universe. There is a strange and fascinating idea in physics that seems to defy common sense, and it is known as length contraction. This concept was first clearly explained by Albert Einstein through his special theory of relativity, which he introduced in the early years of the 20th century. It tells us that the faster something moves through space, the more its length along the direction of a motion appears to shrink. To someone watching from a distance, a fast-moving object, say a spaceship or even a subatomic particle, seems shorter than it actually is when at rest. This idea might sound like a trick of perception, but it is a very real effect predicted by the laws of physics, and it has been confirmed through experiments. The strange part is that it only becomes noticeable when objects are moving at speeds close to the speed of light, which is about 300,000 kilometers per second. At everyday speeds, such as a car on a highway or an airplane in flight, the effect is so tiny that no instrument on Earth could measure it. But as an object approaches the ultimate cosmic speed limit, the speed of light, the contraction becomes extreme and space itself seems to change. Length contraction is one of the most striking consequences of the way motion affects space and time. Before Einstein's theory, people thought of space and time as fixed and unchanging. They believed that no matter how fast something moved, its size and shape stayed the same for all observers. A meter was always a meter, a second was always a second, and everyone everywhere would agree on measurements. But in the early 1900s, Einstein showed that this was not true. According to his ideas, space and time are not separate things. They are part of a single fabric called spacetime. When something moves quickly, the way it experiences space and time changes. To keep the laws of physics consistent for everyone, distances and times adjust depending on how fast an observer or an object is moving. This is where the concept of length contraction comes in. If time slows down for a moving object, then the space it travels through must also change to keep everything in balance. Imagine an astronaut flying through space in a sleek spacecraft. If she could somehow accelerate until she was moving at 90% of the speed of light, she would notice something extraordinary. From her point of view inside the ship, nothing would seem different. Her ship would appear normal, her instruments would measure the same distances, and everything inside would behave as usual. But to someone watching from a planet or a space station far away, her ship would look squeezed in the direction it was travelling. Its length would appear shorter, not because of any damage or compression, but because of the way motion changes the measurements of space. The faster she goes, the greater the contraction becomes. If her ship could move at 99% of the speed of light, it would appear to be only a fraction of its original length. And if she could somehow reach the exact speed of light, her length in the direction of travel would shrink to zero from the point of view of an outside observer. That last idea, that at light speed, length becomes zero, reveals something profound. It shows that light itself, which always travels at that ultimate speed, experiences no passage of time and no distance in the way we do. For a photon, which is a particle of light, the entire universe would seem compressed into a single point. This is one of the reasons why nothing that has mass can ever reach or exceed the speed of light. As something with mass speeds up, its length contracts more and more, and it becomes harder to keep accelerating. The energy required to push it faster increases dramatically, and at the same time, space and time distort in such a way that reaching light speed would require infinite energy. To understand how length contraction makes reaching light speed impossible, it helps to think about how energy and motion are related. In Einstein's famous equation, E=mc², energy and mass are deeply connected. When an object moves faster, its kinetic energy increases, and effectively, its mass increases as well. This does not mean it gains actual material weight, but its resistance to acceleration becomes stronger. Each bit of extra speed takes more and more energy to achieve. When an object is moving at half the speed of light, it already requires enormous amounts of energy to go just a little faster. At 90% of light speed, the energy requirement skyrockets. At 99%, it becomes almost impossible. And at 100%, that is, at the speed of light itself, the energy needed would be infinite. Since no source of energy in the universe can be infinite, this sets a natural barrier that nothing with mass can cross. At the same time, as an object approaches light speed, it undergoes such extreme length contraction that from the viewpoint of an outside observer, the space it occupies nearly disappears. It becomes thinner and thinner in the direction of travel. If one were to measure its front-to-back length, it would look increasingly squashed, while its width and height, those dimensions perpendicular to the motion, would remain unchanged. This one-directional shrinkage is what scientists mean by length contraction. It is not an illusion or a trick of light, but a fundamental property of how space-time behaves under motion. To make the idea clearer, scientists often use the example of a long spaceship flying past an observer. Suppose the ship is 100 meters long when at rest. If it flies past at a speed close to that of light, the observer would measure its length as much shorter, perhaps only 50 meters or even 10 meters, depending on how fast it is going. The ship itself does not feel squashed. The astronauts inside feel perfectly normal. But from the outside, the geometry of the universe makes the ship appear smaller. The difference comes from the fact that both the observer and the moving ship experience time and space differently. For the astronauts, time inside the ship runs slower compared to the observer, and to make the laws of nature remain consistent, space itself contracts in the direction of motion. The idea can be expressed mathematically using the Lorentz factor, which describes how time, length, and other quantities change when objects move at high speeds. The Lorentz factor depends on the ratio between the object's speed and the speed of light. At ordinary speeds, this factor is nearly 1, so no noticeable changes occur, but as speed increases, the factor grows rapidly, causing significant contraction. When speed equals light speed, the Lorentz factor becomes infinite, and length becomes 0. This simple equation reflects one of the most mind-bending truths about the universe. Motion does not just move objects through space, it reshapes space itself. This shrinking of space might sound like science fiction, but it has been confirmed in real experiments. Physicists studying particles moving close to the speed of light inside particle accelerators have observed length contraction in action. Subatomic particles like muons, which naturally exist for only a tiny fraction of a second, live longer when moving at nearly light speed because of time dilation. At the same time, the distances they travel seem shorter to outside observers because of length contraction. In laboratory experiments, scientists can detect that these particles reach the detectors more quickly than they should if space were not contracted. This shows that both time and space adjust themselves according to motion in exactly the way Einstein predicted. The phenomenon is not limited to particles in accelerators. Cosmic rays, high-energy particles that come from space, also provide evidence of these relativistic effects. When cosmic rays strike Earth's atmosphere, they often produce showers of muons. These muons travel toward the ground at nearly light speed. If one were to calculate how far they should travel before decaying based on their short natural lifetime, they should never reach the ground. Yet detectors at the surface consistently record them. The reason is that, from the muon's point of view, the atmosphere is thinner, its length is contracted. The distance it needs to travel seems shorter to it, allowing it to survive the journey. Meanwhile, from our point of view on Earth, the muon's clock runs slower, giving it more time to reach us. Both descriptions are correct, showing that time dilation and length contraction are two sides of the same cosmic coin. In simple terms, length contraction is a kind of adjustment the universe makes to keep the speed of a light constant for everyone. No matter how fast you move, if you measure the speed of light, you will always get the same result, about 300,000 kilometers per second. To maintain that consistency, space and time must shift and stretch. When you move quickly, time slows down for you, and the distance in front of you becomes shorter. That way, even though your motion changes your experience of space and time, the speed of light never changes. This is one of the most astonishing and beautiful aspects of Einstein's theory. It shows that space and time are not rigid containers, but flexible dimensions that respond to motion. If one tries to think about what happens as an object accelerates closer and closer to light speed, the picture becomes even more dramatic. At first, the object behaves almost normally. At 10% or even 20% of light speed, nothing unusual happens. At 50%, very small effects begin to appear, but they are still almost impossible to detect. However, at 90%, the changes become measurable. The object's mass appears greater, time slows significantly for it, and its length contracts noticeably in the direction of travel. At 99%, these effects become extreme. The object's length may appear only a tenth of its original size, and at 99.9%, the contraction becomes so severe that the object is nearly flattened from the perspective of someone watching from rest. If we could imagine an object somehow pushed to 99.999% of light speed, its length in the direction of motion would be reduced by a factor of about 70. That means a spaceship that is 100 meters long, when stationary, would appear less than 2 meters long to an outside observer. The passengers inside, however, would feel no difference. Their world would seem normal, and they would see the universe outside distorted in the opposite way. Distances in the direction of motion would appear shorter, and clocks outside would seem to tick faster. This difference in perception is not due to illusion, but because each observer experiences space and time differently depending on their state of motion. As the speed continues to rise, the shrinking of space becomes a physical wall. Since the object's own dimensions are getting smaller in the direction it moves, every step of acceleration demands more energy to compress both its time and space even further. The fabric of space-time resists this compression. Just as it would take infinite energy to make time stop completely, it would also take infinite energy to make space shrink completely. That is why light speed is not only a speed limit, it is the ultimate boundary where our familiar ideas of distance and duration no longer make sense. In the world of light, these concepts dissolve entirely. For photons, there is no before or after, no here or there. They are created and absorbed, and for them, those two events happen instantly, no matter how far apart the points may be in our reference frame. To us, light may travel for billions of years across the universe, but from the photon's own perspective, that journey takes no time at all, and the distance it crosses does not even exist. This is because, at that unimaginable speed, space and time themselves lose their meaning. This behavior also helps explain why no material object can ever catch up with light. As an object accelerates and its length contracts, its mass energy increases, demanding more power for each small gain in speed. At the same time, the universe seems to close in around it. The distances ahead become shorter, and time slows so much that from the object's perspective, the universe's clocks nearly stop. The closer it gets to light speed, the harder it becomes to gain any more speed at all. Even if one poured all the energy in the universe into accelerating that object, it would never quite reach the magic number of 300,000 kilometers per second. The contraction of space, the dilation of time, and the increase in energy all work together to maintain that cosmic barrier. Length contraction also leads to curious and sometimes puzzling situations when one tries to think of simultaneous events. Suppose a long train moving very close to light speed passes through a tunnel that is shorter than the train at rest. From the viewpoint of an observer standing beside the tunnel, the train appears contracted, it fits inside easily for an instant. But from the viewpoint of a person on the train, the tunnel is the one that appears shorter, and the train never fully fits inside at any moment. Both perspectives are correct because each observer's measurement of space and time is equally valid in their own frame of reference. This so-called ladder paradox shows that length contraction is not about one observer being right and another wrong. It is about how reality itself changes depending on motion. This relativity of space challenges our everyday understanding. We're used to thinking that if something measures 1 meter for one person, it must measure 1 meter for everyone. But in the universe that Einstein described, measurements of length depend on how fast the measurer is moving, relative to what they are measuring. There is no single universal ruler that works for all situations. The only constant is the speed of light itself, which ties all these differences together in a consistent way. In the early days of physics, before Einstein's ideas, scientists like Hendrik Lorentz and George Fitzgerald had already proposed something similar to length contraction to explain puzzling results from experiments. One of these was the Michelson-Morley experiment of the late 19th century, which tried to detect the motion of Earth through the so-called ether, a medium once thought to fill space. The experiment found no difference in the speed of light in any direction, suggesting that light's speed was the same everywhere. To explain this, Lorentz and Fitzgerald proposed that objects moving through the ether might contract in the direction of motion, making the differences impossible to detect. Later, Einstein showed that the contraction did not depend on any ether at all. It was simply a natural result of how spacetime itself behaves. Today, length contraction is a cornerstone of modern physics. It is built into everything from particle accelerators to global positioning systems. The satellites that make GPS work orbit Earth at high speeds, and their clocks and positions are affected by both time dilation and length contraction. Engineers must account for these effects to make sure the systems stay accurate. Without the corrections provided by relativity, GPS would quickly drift out of sync, leading to large errors in positioning. This shows that even though the effects of relativity seem distant and abstract, they have very real consequences for technology and for our understanding of how the universe works. The concept of space shrinking with speed also changes how we think about journeys through the cosmos. For travelers moving close to the speed of light, distances that seem impossibly vast to us could appear much shorter to them. A trip to a star system 10 light-years away might take only a few years from the traveler's point of view because of both time dilation and length contraction. To observers on Earth, however, the journey would still take 10 years or more. This idea has inspired countless works of science fiction and scientific thought experiments, showing how relativity reshapes our concept of distance, duration, and even aging. If a spacecraft could somehow travel at 99.9% of light speed, its crew would experience the universe in a dramatically different way. From their viewpoint, the stars ahead would seem closer together, and the space between them would shrink. A journey across the galaxy might feel like it takes only a few years to them, while billions of years could pass outside. To an observer watching from Earth, the ship would appear flattened and slowed, while for the travellers, the cosmos itself would appear contracted. This strange duality shows how deeply motion affects our sense of space, even though these effects are beyond our normal experiences. Space is not a rigid stage on which events happen. It bends, stretches, and shrinks depending on motion. The more an object moves, the more the universe seems to reshape itself around that motion, balancing time and distance so that the speed of light remains the same for everyone. The closer one gets to that ultimate speed, the more the world itself seems to fold up, as though space and time are conspiring to prevent anything from crossing that final boundary. Length contraction, therefore, is not just a curiosity of physics. It is a window into the true nature of reality. It shows that our familiar world of fixed distances and steady clocks is only an approximation, one that works well at low speeds, but breaks down when we move too fast. At the deepest level, the universe is far stranger and more flexible than it seems. The distances we think are absolute are in fact relative. The spaces we believe are empty are filled with structure. The faster we move, the more the universe reveals its hidden nature, until at the ultimate speed, space itself disappears. Through the study of length contraction, physicists have learned that motion and geometry are inseparable, that space and time are not constant but connected, and that the universe guards its secrets with subtle, unbreakable laws. Every fast-moving particle, every beam of light, every cosmic ray streaking through the void carries within it a silent message about these laws. In the vast and mysterious universe, light is not only the fastest traveller known to exist, but also a kind of ultimate speed limit written into the very fabric of reality. It moves through space at nearly 300,000 kilometers every second, a velocity so enormous that it defies ordinary human understanding. This number is not merely a scientific curiosity, it is a cosmic rule. It means that nothing carrying mass, no matter how small or powerful, can ever reach or surpass the speed of light. The reason for this is not because scientists lack strong enough rockets, or because technology is still developing. It is because the laws of physics themselves create what can be described as an infinite energy barrier that stops anything with mass from ever crossing that boundary. The concept comes from Albert Einstein's special theory of relativity, introduced in the early years of the 20th century. His work forever changed how humanity thinks about space, time, and motion. Before Einstein, it was thought that if one simply pushed harder, added more energy, or built a faster engine, one could make an object move faster and faster without end. There seemed to be no fundamental limit to how fast something could go. But Einstein showed that this view was incomplete. He discovered that as an object's speed increases, its mass effectively increases too, and this creates a problem. The faster the object moves, the harder it becomes to accelerate it further. The energy needed to push it faster does not rise in a straight line. It rises exponentially, and near the speed of light, it grows toward infinity. To understand why this happens, it helps to look at the mathematical relationship between energy, mass, and motion that Einstein revealed. His most famous equation, E, mc2, connects energy, E, and mass, m, with the speed of light, c. The equation tells us that mass and energy are two sides of the same thing. Mass can be turned into energy, and energy can become mass. But when an object with mass begins to move faster, it doesn't simply gain speed, it also gains energy that contributes to what is called its relativistic mass. This means that from an outside observer's perspective, the moving object appears to grow heavier the faster it goes. If we dig deeper into the mathematics of relativity, we find that the total energy of a moving object can be written as E shan g mc2. Here, the Greek letter gamma, dre, represents a quantity called the Lorentz factor, which depends on how close the object's speed, v, is to the speed of light, c. The Lorentz factor is defined as dr/1 st of v2c2. At first, this may seem like just another complex equation, but it reveals something astonishing about the structure of the universe. The denominator, the part under the square root, contains the expression 1 v2c2. As the object's speed, v, gets closer to the speed of light, c, the term v2c2 becomes larger and larger. If the object were to reach the speed of light, v2c2 would become 1, and 1 c2c2 would become 0. The square root of 0 is 0, and dividing 1 by 0 is mathematically undefined, it tends toward infinity. What this means is that the Lorentz factor, g, grows without limit as an object's speed approaches the speed of light, and because g multiplies the rest mass and the speed of light squared in the energy formula, the total energy required to move the object also grows toward infinity. In simple words, no matter how powerful the source of energy, it would never be enough to make a massive object reach light speed. To put this in perspective, think of an object starting from rest. At very low speeds, the Lorentz factor g is almost equal to 1, so the object behaves normally according to classical physics. But as the speed increases, say to half the speed of light, 1 becomes about 1.15. The energy needed to keep increasing its speed becomes slightly greater than expected. At 90% of light speed, ρ becomes about 2.3. That means it takes more than twice as much energy as before to achieve the same increase in speed. At 99% of light speed, g jumps to about 7. To reach 99.99%, g skyrockets to more than 70. Each small fraction of additional speed demands an enormous and ever-growing amount of energy. This shows how nature resists any attempt to push matter to the cosmic limit. The closer one gets to light speed, the more energy the object absorbs, yet the returns grow smaller and smaller. The energy keeps rising while the increase in speed becomes almost negligible. The equations themselves reveal a kind of built-in resistance that cannot be overcome. At light speed itself, the required energy becomes infinite, and infinity is not something that exists in the physical world. No engine, no star, no explosion, and no conceivable source of energy could ever provide an infinite amount of power. This strange connection between mass, energy, and speed gives us a picture of a universe that protects its own limits. It is as if the laws of nature themselves prevent the tearing of space-time fabric by blocking anything from reaching the sacred speed of light. But this is not just an abstract rule, it has real, measurable effects. For example, scientists who study particles in giant accelerators, like those at CERN, have seen this effect directly. Protons, which are subatomic particles with mass, are accelerated to speeds incredibly close to that of light using powerful magnetic fields. The machines give them enormous amounts of energy, enough to make them move at more than 99.999999% of the speed of light. Yet no matter how much energy is added, they never quite reach light speed. Their kinetic energy continues to increase, but their velocity stops just short of the cosmic barrier. In fact, most of the added energy goes into increasing the particle's effective mass, not its speed. This is a clear demonstration of the infinite energy barrier in action. The same idea explains why light itself, which moves exactly at the speed of light, must have zero rest mass. Photons, the particles that make up light, have no mass when they are stationary because if they did, even the tiniest mass would require infinite energy to make them travel at light speed. Since they move at that speed naturally, they must be fundamentally massless. This is why light can zip through space effortlessly, while any object that has even a small amount of mass is forever confined to slower speeds. The infinite energy barrier is not just a mathematical trick, it's a reflection of how the universe keeps balance. It ties deeply into the way time and space are woven together. As an object's speed increases, not only does its energy requirement explode, but time itself slows down for it. From the perspective of a stationary observer, the fast-moving object experiences time at a slower rate. This is time dilation, another part of Einstein's theory. The faster something goes, the slower time passes for it, and its mass increases as well. So when physicists say it would take infinite energy to reach light speed, they are also saying that, at that point, time would stop for the object, and its mass would become infinite. The word infinite is not used lightly in physics. It means a quantity that cannot be reached or even represented by any physical process. For everyday speeds, like cars, airplanes, or even rockets, the difference between Newton's classical mechanics and Einstein's relativistic equations is tiny. But once an object's speed becomes a significant fraction of the speed of light, the difference becomes enormous. A spacecraft travelling at half the speed of light would already require mind-bending amounts of energy, far beyond what humanity could currently generate. To double that speed would demand not double the energy but many times more. If one were to calculate how much energy it would take to move something like a 1-ton spacecraft to near light speed, the results would be staggering. Using the relativistic energy equation, even to reach 99.9% of light speed, the amount of energy required would be equal to the total energy output of entire civilizations. The closer we try to get to light speed, the greater the energy grows, climbing upward with no end. This is the meaning of the infinite energy barrier. The universe allows you to approach the boundary but never to touch it. To better grasp how this energy behaves, we can look at how kinetic energy is defined in relativity. In classical physics, kinetic energy equals 1/2 of the mass times the velocity squared, or 1 to 2 mv2. But in relativity, the kinetic energy, k, of an object is given by k sembrunst g 1 mc2. This means the kinetic energy depends on the Lorentz factor, g. At low speeds, g is nearly 1, so k behaves just like in Newton's world. But at speeds near light, g becomes extremely large, so k rises sharply. Let's examine a few examples. At 1/10 of light speed, the kinetic energy is only about 0.5% of the rest mass energy, mc2. At half the speed of light, it is about 1/3. At 90% of light speed, it becomes more than twice the rest mass energy. And at 99.9%, it is more than 20 times greater. Each small increase in speed near light speed multiplies the required energy many times over. The numbers explode rapidly, emphasizing the sheer impossibility of ever reaching that ultimate limit. This exponential rise has fascinating consequences. It tells us that acceleration is not an equal process. It becomes harder and harder as one moves faster. Every extra bit of velocity comes at a greater cost in energy. In everyday life, we're used to adding speed linearly. A car burns fuel, it goes faster. A rocket expels propellant, it accelerates more. But the universe does not allow this forever. There comes a point where energy no longer translates efficiently into speed. Instead, it begins feeding into mass, time distortion, and the warping of spacetime itself. In theoretical discussions, one might imagine a civilization advanced enough to gather energy from stars, galaxies, or even black holes. Even such a civilization would still face the same universal law. The infinite energy barrier applies everywhere, from the smallest particle to the largest spaceship. It is not a technological problem, it is a structural rule of the cosmos. There are some ways scientists and theorists have tried to think around this limitation. Some propose using warp drives, where instead of pushing an object through space faster than light, space itself is made to contract in front of the craft and expand behind it. In this way, the craft would not technically move faster than light relative to its local space, but would still cover enormous distances quickly. Yet even these ideas face tremendous challenges, including the need for negative energy or exotic matter, which have never been observed in usable quantities. All these concepts highlight the same truth. Direct acceleration to light speed is impossible because of the infinite energy barrier built into nature. In high-energy physics, this barrier has another subtle effect. When particles are accelerated near light speed, their mass increase also affects how they interact with magnetic and electric fields. Since heavier particles are harder to deflect, the machinery required to control their path must use stronger and stronger fields. This adds another layer of difficulty. The energy used not only goes into accelerating the particles, but also into maintaining control over their direction and stability. Particle physicists spend enormous effort designing magnets powerful enough to handle such near-light speed motion, and even then, they can never actually reach the barrier itself. On the cosmic scale, there are natural phenomena that push matter close to this limit. Jets of particles ejected from supermassive black holes, for example, have been measured moving at speeds extremely close to light speed. Yet even in those extreme environments, where gravity, magnetism, and energy are beyond anything humans can create, the particles never truly reach the speed of light. The same mathematical law governs them all. The faster they go, the harder it becomes to push them further, and the energy demands grow so enormous that nature itself seems to refuse it. The infinite energy barrier also explains the stability of the universe. If objects could exceed light speed, many of the foundational principles of causality, meaning cause and effect, would break down. Events could happen before their causes, and time order would lose meaning. The laws of physics seem designed to prevent that. The infinite energy requirement acts as a safeguard, keeping reality consistent and preventing paradoxes that would arise if information or matter could move faster than light. Einstein's equations, elegant yet strict, encode this protection deep within their structure. The denominator, 1 v2c2 in the Lorentz factor, not only ensures that no massive object can reach light speed, but also preserves the fundamental order of the universe. If v ever equaled c, the math would collapse, and physical predictions would no longer make sense. This mathematical wall is not an accident. It reflects a deeper truth about how space and time work together as one continuous fabric called spacetime. This infinite barrier creates a fascinating balance between what is possible and what is not. Light, being massless, is free to travel at the ultimate speed. Matter, possessing mass, is bound below that speed forever. Yet the two are deeply connected through energy. Mass can become energy, and energy can become mass, but never in a way that breaks the speed limit. It is as if light and matter exist on opposite sides of a cosmic line that can never be crossed. Even though the idea of infinite energy sounds abstract, it has very practical meaning. It tells scientists how to design particle accelerators, how to plan interstellar missions, and how to understand the structure of galaxies. It explains why cosmic rays, particles from deep space moving at incredible speeds, still fall just short of the light barrier, no matter how powerful the processes that created them. The same principle holds everywhere in the cosmos, from the smallest atom to the largest star. The infinite energy barrier, then, is not a physical wall floating in space, but a mathematical boundary built into the equations that describe reality. It is a line written into the fabric of the universe itself, ensuring that mass and energy behave in harmony. Every attempt to cross it leads only to greater resistance, greater energy demands, and deeper distortions of time and space. It is both a limit and a law, both a challenge and a mystery, showing that even in the vast freedom of the cosmos, there are boundaries that nothing can break. If one were to look at the entire universe through this idea, one might see that it helps explain why the cosmos behaves the way it does. It ensures stability, keeps causality intact, and defines the difference between light and matter. Without it, everything would collapse into chaos, and the fundamental structure of existence would no longer hold together. The infinite energy barrier stands as one of nature's most powerful truths, quietly governing the motion of every star, planet, and particle, making sure that while energy and mass can dance together endlessly, they can never dance past the speed of light. Throughout the history of science, there has always been a deep fascination with speed. Humanity has spent centuries trying to go faster, from the first horse-drawn carts to modern spacecraft that can travel thousands of kilometers per hour. But even as our technology continues to advance, one limit stands unbroken: the speed of light. This cosmic limit, about 300,000 kilometers per second, has been firmly established by modern physics as the ultimate boundary that no object with mass can ever cross. Yet, in the imagination of physicists and thinkers, the question lingers: what if something could go faster than light? What if there existed particles that did not just approach light speed but surpassed it? Out of this daring question came the concept of tachyons, hypothetical particles that travel faster than light, always racing beyond the reach of ordinary matter and our familiar laws of physics. The term tachyon comes from the Greek word tachys, meaning swift. It was chosen deliberately to describe these imagined particles that would move with unimaginable speed. The idea of tachyons first appeared in the mid-20th century, a period when scientists were exploring the limits of Einstein's special theory of relativity and wondering whether the speed of light truly represented an unbreakable wall. According to relativity, no object with mass can ever reach, let alone exceed, the speed of light, because doing so would require an infinite amount of energy. However, Einstein's equations did not explicitly forbid something from already existing beyond that barrier. That subtle loophole inspired a new class of thought experiments. What if certain particles existed that never travelled slower than light, but always remained faster than it? In the early 1960s, several physicists, including Gerald Feinberg, began exploring this strange possibility. They proposed that if such particles existed, they would possess unusual properties that set them apart from every other kind of matter known. These particles were named tachyons, and they would have imaginary mass. A concept that sounds mysterious but follows from the mathematics of relativity. In Einstein's famous equation, E2 = mc2 plus pc2, if a particle's velocity exceeded the speed of light, the term under the square root would become negative, which mathematically results in an imaginary number. Rather than treating this as an error, some physicists suggested that perhaps such quantities could correspond to real, physical entities, tachyons, whose behavior would lie forever on the far side of the light-speed barrier. The existence of tachyons would completely change our understanding of time, space, and causality. For ordinary particles, often called bradyons, which move slower than light, time flows forward in a way we can understand, cause precedes effect, and events unfold in a predictable order. But for tachyons, the situation would be very different. In some reference frames, a tachyon might appear to move backward in time. That means that if you could somehow detect a tachyon, it might seem to arrive before it was even emitted. This deeply strange possibility led many scientists to question whether such particles could exist at all without creating paradoxes in the universe. The very idea of travelling backward in time creates problems for logic and physics alike. For instance, if information could be sent faster than light using tachyons, it might allow messages to be received before they were sent. This could lead to what physicists call causality violation, where cause and effect are reversed. In our ordinary experience, such things never happen. You cannot read a book before it is written, or hear an echo before the sound is made. Yet tachyons, at least according to theory, would allow such reversals to occur. This troubling consequence is one of the reasons why tachyons remain firmly in the realm of speculation rather than accepted science. Still, the concept continues to intrigue both scientists and science fiction writers. Tachyons often appear in popular stories as a way to explain faster-than-light communication, time travel, or instantaneous action across vast distances. In these imaginative settings, tachyons serve as the perfect solution to the problem of limited speed. They can send signals across galaxies or even between different times. Although such uses are purely fictional, they help to keep the idea of tachyons alive in the public imagination, symbolizing humanity's endless curiosity about what lies beyond our physical limits. From a more technical perspective, physicists have explored what properties tachyons would have if they were real. Because they would always move faster than light, they could never slow down to light speed, just as ordinary particles can never accelerate up to it. In a sense, the light-speed barrier separates the universe into two distinct regions, one for slower-than-light particles and one for faster-than-light ones. The two regions do not overlap. A tachyon could never be slowed down enough to become a normal particle, and a normal particle could never be accelerated enough to become a tachyon. According to the equations, as a tachyon's energy decreases, its speed would actually increase, and as its energy increases, its speed would decrease, an exact opposite of how ordinary particles behave. This counterintuitive relationship arises because of the negative mass-squared term in their equations. For example, when you accelerate an ordinary object, you add energy and it moves faster. But with tachyons, adding energy would make them slow down closer to the speed of light, though never reaching it, while losing energy would make them move faster, even farther beyond the light barrier. This bizarre behavior is part of what makes tachyons so difficult to fit into known physics. In the early years of theoretical exploration, some physicists wondered if tachyons might even play a role in real physical processes. Could they be involved in radioactive decay? Could they somehow explain certain cosmic phenomena that seem to defy explanation? These questions inspired experiments and searches for any signs of particles that behaved like tachyons. Yet, despite decades of effort, no evidence has ever been found. All observations of particles from electrons to protons to neutrinos confirm that they obey the cosmic speed limit. Even in cases where particles appear to exceed light speed, further investigation has always shown that the effect is an illusion. A well-known example occurred in the year 2011, when a team of scientists working on the Opera experiment reported that neutrinos had been detected travelling slightly faster than light. The announcement caused worldwide excitement, as it seemed to suggest that tachyon-like behaviour might finally have been observed. However, after months of careful review, the result was traced to a faulty cable connection and timing error in the equipment. Once corrected, the measurements showed that the neutrinos were indeed moving below light speed, as expected. This incident reminded everyone just how delicate such measurements are and how strict the laws of relativity appear to be. While tachyons have not been observed in nature, they sometimes appear in certain areas of theoretical physics as mathematical tools. For example, in quantum field theory and string theory, a tachyonic field can appear in the equations. In these contexts, however, the word tachyon does not refer to a real faster-than-light particle, but rather to a mathematical sign that indicates instability. When a system's energy equation shows a tachyonic term, it means the current state is unstable and will eventually settle into a more stable configuration. This idea is often used in discussions of how the early universe may have evolved from a high-energy, unstable state into the more stable one we observe today. The appearance of tachyonic fields in string theory, especially during its early development in the 1970s, caused much debate. At first, some researchers worried that this might mean the theory predicted real tachyons, which would be problematic, but later work showed that these tachyonic terms could be interpreted in a different way, as a sign that the vacuum or the basic state of the system needed to be redefined. Once that was done, the instability disappeared and the theory became consistent again. This usage of tachyons is symbolic rather than physical, showing how ideas that once seemed paradoxical can still play useful roles in abstract mathematical theories. Despite their speculative nature, the idea of tachyons continues to raise fascinating questions about the limits of physics. For instance, what would the universe look like from the perspective of a tachyon? Since nothing in our universe can move faster than light, our sense of space and time depends on signals that travel at or below that speed. But if a being could travel faster than light, its experience of time and space would be completely different. From its viewpoint, events that we consider separate and sequential might appear to happen all at once. Distance and duration could lose their ordinary meaning. This strange world of reversed time and overlapping events stretches the imagination and challenges our understanding of reality itself. Some theoretical physicists have even explored the idea that tachyons might exist in a hidden or separate realm of the universe, where different physical laws apply. In such a realm, the speed of light might not be the upper limit, but a lower one, meaning that everything would naturally move faster than light. If such a parallel tachyonic world existed, it would be forever disconnected from ours because no signals could cross the light speed barrier in either direction. That would make it completely invisible and undetectable from our point of view, existing as a mathematical curiosity rather than a physical reality. Even though such concepts remain beyond current scientific reach, they serve an important purpose in physics by testing the limits of our theories. Science often progresses not only by confirming what is true, but also by exploring what might not be. Theoretical constructs like tachyons push the boundaries of understanding and force scientists to examine whether the laws we take for granted are truly universal or merely approximations. They remind us that our picture of the universe, no matter how detailed, may still be incomplete. There is also an interesting connection between tachyons and the concept of imaginary numbers in mathematics. In everyday arithmetic, we deal with real numbers, those that represent measurable quantities like length, mass, or time. But in higher mathematics, imaginary numbers are used to describe complex relationships that cannot be expressed using only real values. Similarly, tachyons represent a kind of imaginary matter, something that might exist in the mathematical sense but not in the tangible world. The parallel between imaginary numbers and imaginary mass highlights how mathematics can suggest possibilities that nature does not necessarily realize. If tachyons did exist, they might also have curious effects on gravity and the structure of spacetime. Some theoretical work has examined whether tachyons could generate gravitational fields or even warp space in unusual ways. Because they would move faster than light, their energy would be distributed differently from that of normal matter. This could, in theory, create distortions that might resemble shock waves in spacetime, similar to how an aircraft moving faster than sound creates a sonic boom. In this case, a tachyon might produce a luminal boom, a burst of energy as it crosses the threshold of light-speed interaction. While no such phenomenon has ever been observed, the idea demonstrates how tachyons could inspire new thinking about energy and motion on a cosmic scale. The possibility of using tachyons for communication has also been a recurring topic in scientific discussion. If they could carry information faster than light, it would be possible to send signals across enormous distances in an instant, connecting different parts of the universe without delay. However, as mentioned earlier, this would violate causality, meaning that effects could precede their causes. To prevent such contradictions, most physicists agree that faster-than-light communication cannot occur, at least not within the framework of known physics. Some theories suggest that if tachyons exist, they might interact so weakly with ordinary matter that they could never be used to transmit information in a controlled way, effectively keeping the universe safe from paradoxes. Over the decades, scientists have also considered whether tachyons might explain certain unexplained cosmic phenomena, such as bursts of radiation or mysterious cosmic rays that seem to carry enormous energy. However, none of these observations have ever provided concrete evidence for tachyons. Every time an unusual signal has been detected, further analysis has shown that it can be explained by conventional physics without invoking faster-than-light particles. This consistency strengthens the case that tachyons, if they exist at all, do not play a noticeable role in the universe we observe. Another interesting idea connected to tachyons is their potential connection to quantum mechanics. In quantum theory, particles can sometimes behave in ways that defy classical intuition, appearing to be in multiple places at once or passing through barriers they should not be able to cross. Some physicists have wondered if tachyons could exist as quantum states rather than physical particles, influencing probabilities rather than acting directly in space. In this view, tachyons might not be real entities, but instead mathematical symbols for faster-than-light correlations that occur in quantum entanglement. However, experiments on entanglement have shown that while quantum information appears to spread instantly, no actual energy or matter moves faster than light. Thus, even quantum physics seems to preserve the cosmic speed limit. Throughout the second half of the 20th century and into the 21st, tachyons have remained a recurring topic in both physics and philosophy. They challenge scientists to think about the meaning of speed, time, and causality at the deepest level. Even though they have not been observed, they continue to appear in lectures, research papers, and speculative discussions. For many, tachyons symbolize the spirit of scientific curiosity, the willingness to ask "what if," even when the answer might be impossible. There is a poetic quality in the idea of tachyons. They represent the unreachable, the beyond, the part of the universe that always escapes our grasp. Just as light defines the boundary of what we can see, tachyons would define the boundary of what we can never touch. They move forever faster than the fastest thing we know, forever outside the reach of our instruments, and perhaps forever outside the reach of reality itself. Yet by imagining them, we learn more about the universe and about the rules that make it coherent and stable. If the universe truly forbids tachyons, that prohibition tells us something profound about how deeply time and space are linked. The cosmic speed limit is not just a number, it is the foundation that keeps cause and effect in order, ensuring that history unfolds in a single direction. Tachyons, with their imaginary mass and backward flow of time, serve as a reminder of what would happen if that foundation were broken. They show us, through their very impossibility, why the universe must be as it is. At the same time, the concept continues to evolve. In modern theoretical frameworks, physicists still use tachyon-like fields as part of their mathematical explorations. In string theory, for example, the appearance and disappearance of tachyonic terms can help describe how strings stabilize, or how energy transitions from one state to another. Even though no real tachyon has ever been found, the mathematics they inspired remains useful and relevant, illustrating how even speculative ideas can shape the progress of science. Through all these discussions, tachyons continue to stand at the edge of the possible, a reminder of the thin boundary between reality and imagination in the world of physics. The search for them, though it may never succeed, reveals the human desire to understand the universe completely, to push every limit, and to ask every forbidden question. They are symbols of our curiosity about speed, time, and the deepest structure of existence, always racing ahead in theory even if they remain forever beyond reach. In the great structure of the universe, everything that moves through space is bound by one remarkable rule: nothing with mass can ever reach or exceed the speed of light. This law, first clearly expressed by Albert Einstein in the early 20th century, is one of the strongest and most unbreakable truths in physics. Yet, there is a small group of special travelers in the universe who do not obey this restriction in the usual way. These are the massless particles, beings of pure energy that move effortlessly at the ultimate speed of light, never slower and never faster. Among them, photons, the particles of light, stand out as the most familiar and most important. They fill the universe, carrying energy, warmth, and information across billions of kilometers of empty space. To understand why these particles are so different from the rest of the universe's inhabitants, we must first recall what mass means in physics. Every object that has mass resists changes in its motion. The more massive something is, the harder it is to push, pull, or accelerate. This is why a small pebble is easy to throw, but a mountain cannot be moved no matter how hard one tries. Mass is not only a measure of how much matter something contains, it also determines how it interacts with space, time, and energy. In Einstein's theory of special relativity, energy, mass, and motion are all connected. The famous equation E, mc2, shows that mass and energy are two forms of the same thing. When something with mass speeds up, it gains energy, and as it gains energy, its effective mass increases. This makes it harder and harder to accelerate as it approaches the speed of light. The energy required to push it faster keeps growing without limit, reaching infinity at the speed of light. This is why nothing that has mass can ever reach that speed. There simply isn't enough energy in the universe to make that happen. But photons and other massless particles are entirely different. They do not have rest mass. This means that even when they are not interacting with anything, their mass is exactly zero. Because they have no rest mass, they do not experience time or motion in the same way that massive objects do. In fact, they cannot exist at rest at all. A photon that stops moving would not exist because a massless particle at rest has no energy, no frequency, and no reality. It is only by moving at the speed of light that a photon can exist. That speed is not a choice or a limit for it. It is its natural state of being. From the very first moment a photon comes into existence, when an atom releases it, or when a charged particle is accelerated, it instantly travels at light speed. There is no period of acceleration or gradual increase in velocity. It is born moving at full speed, roughly 300,000 kilometers per second, and it never slows down. This is not because something pushes it or forces it to move that way, but because the laws of the universe demand it. The structure of spacetime itself allows only two kinds of existence: objects with mass that move below light speed, and objects without mass that always move at light speed. There is no middle ground between the two. Photons are the best known of these massless travelers, but they are not alone. Gluons, the particles that carry the strong nuclear force, are also massless in theory, though they behave differently because they are trapped inside atomic nuclei and cannot move freely like photons. Gravitons, the hypothetical particles that would carry the force of gravity if gravity were a quantum force, are also believed to be massless. If they exist, they too would travel at light speed, rippling through space-time just like light does through space. Even certain exotic theoretical particles, such as hypothetical axions or the quantum excitations of fields that have no mass, share this property of eternal unchanging speed. To understand this behavior more deeply, it helps to think of what light really is. Light is not just something that shines. It is a vibration, a wave traveling through the electromagnetic field that fills all of space. This field is made up of electric and magnetic components that constantly create and cancel each other as they move forward. The photon is the smallest possible piece of that field, the smallest quantum of light. Because this field has no mass itself, its disturbances, the photons, cannot have mass either. The electromagnetic field's natural vibrations move at one fixed speed through space, and that speed is what we call the speed of light. It is built into the very fabric of the universe, determined by the properties of space and time themselves. In mathematical terms, the speed of light can be found from two fundamental constants of nature: the electric permittivity and the magnetic permeability of space. When these are combined, they give a number that equals the speed of light. This means that light's speed is not just a random value. It is a reflection of how space and time are structured. The photon's motion is an automatic result of these universal properties. Since it has no mass, there is nothing in its nature that can slow it down or give it inertia. It simply moves through the universe as fast as space allows anything to move. Another fascinating fact about photons is that they experience no passage of time. For everything that has mass, time flows from past to future. But for a photon, which always travels at light speed, time stands still. From its own point of view, which is difficult to imagine, its journey from one side of the universe to the other happens instantly. While billions of years may pass for us as light travels from a distant galaxy, for the photon itself, no time at all passes between its creation and its arrival. It is as though the photon exists only in the moment of its motion, never aging, never slowing, and never resting. This property also helps explain why light can travel across the vastness of space without losing speed. Unlike a car that slows due to friction, or a planet that moves in orbits due to gravity, light has no mass and no resistance to motion in empty space. It does not lose energy by slowing down, although it can lose energy by spreading out or by redshifting as space itself expands. Even after travelling billions of light years, a photon still moves at the same incredible speed. When light passes through materials such as glass, air, or water, it appears to slow down. But this slowing is not because the photons themselves are moving slower. Instead, the photons are constantly being absorbed and re-emitted by atoms in the material, which delays their progress. Between interactions, they still move at light speed. This is why light can bend or refract when it enters a new medium. It is the change in its path caused by the different interactions with matter, not a true reduction of its fundamental speed. Massless particles also reveal something profound about the relationship between energy and momentum. In the case of massive objects, energy is related to both mass and motion. But for a massless particle like a photon, energy is determined only by its frequency. The higher the frequency of the light, the more energetic the photon. Blue light, for instance, has more energy per photon than red light, and gamma rays have vastly more energy than visible light. Yet, regardless of how energetic or weak a photon is, it always travels at the same speed. There is no slow photon or fast photon, only photons with different amounts of energy but identical velocity. This constancy is deeply connected to Einstein's theory of relativity. In relativity, the speed of light acts as a universal constant, the same for all observers no matter how fast they are moving. This means that even if you are travelling near light speed and you shine a flashlight forward, you will still measure the light from your flashlight as moving away from you at light speed. It is impossible to add to or subtract from that speed. This strange fact is one of the reasons why space and time must warp and stretch to preserve this rule. The universe adjusts time and distance rather than allowing light to change its speed. Because massless particles always travel at light speed, they play a key role in defining how spacetime behaves. In physics, the path that light takes through space and time, called a light-like or null trajectory, sets the structure of causality. No information or effect can move faster than light, and nothing can influence an event outside of its light cone. This means that massless particles define the very limits of what can happen in the universe and when it can happen. Without them, the geometry of spacetime would have no clear direction or boundary. Massless particles are also at the heart of many forces in nature. The photon carries the electromagnetic force, allowing charged particles to interact across empty space. The gluon carries the strong nuclear force, binding quarks together inside protons and neutrons. The theoretical graviton would carry the gravitational force, causing masses to attract across the cosmos. Each of these force carriers shares the property of being massless or nearly so, because the forces they represent have infinite or long-range effects. If these particles had mass, their forces would fade quickly with distance, as happens with the weak nuclear force, whose carriers, the W and Z bosons, are massive. This distinction between massive and massless force carriers explains much about how the universe works. The electromagnetic force can reach across the solar system, while the strong force can hold together only the insides of atomic nuclei. Gravity can shape galaxies, while the weak force can only affect particles during radioactive decay. The range of each force depends directly on whether its carrier particle has mass. Massless particles can reach forever, massive ones cannot. Even though photons have no mass, they still carry energy and momentum. This means they can exert pressure and transfer momentum to other objects when they strike them. This phenomenon is known as radiation pressure, and it can have surprising effects. The tails of comets, for example, are pushed away from the sun by the pressure of sunlight. Spacecraft equipped with light sails can use this gentle but continuous force to travel through the solar system without any fuel. The light that has no mass can still move worlds, demonstrating the strange power that comes from pure energy in motion. The discovery that light consists of massless particles was one of the great achievements of modern physics. Before the 20th century, scientists believed light was purely a wave. Then, in the early 1900s, experiments showed that light could also behave like particles, packets of energy that could knock electrons off metal surfaces, a phenomenon known as the photoelectric effect. Albert Einstein explained this effect by proposing that light consists of quanta, later called photons. These photons have no rest mass but carry energy in proportion to their frequency. This explanation helped establish the foundation of quantum mechanics and earned Einstein the Nobel Prize in Physics in the year 1921. This new understanding revealed that the universe was far more flexible than anyone had imagined. Waves could behave like particles, and particles could act like waves. Photons showed that energy and matter were deeply connected, and that even something without mass could carry force, information, and structure. The behavior of massless particles continues to be central to both quantum mechanics and relativity, two theories that together describe almost everything we know about the physical universe. Another remarkable aspect of photons and other massless particles is that they cannot be slowed down or sped up by any force. Gravity can bend their paths, but it cannot change their speed. When light passes near a massive object, such as a star or black hole, its direction curves because space itself is curved. This bending of light by gravity, known as gravitational lensing, has been observed countless times by astronomers. Even though the light's path changes, its speed relative to the local structure of space remains constant. It continues to move along the shortest possible path through curved spacetime at the same unchanging speed. In quantum field theory, the existence of massless particles like photons arises naturally from the symmetries of the laws of nature. For example, the electromagnetic field has a type of symmetry known as gauge invariance. This symmetry requires that the photon be massless. If it had mass, the symmetry would be broken, and the laws of electromagnetism would no longer work as they do. This connection between symmetry and masslessness is one of the most beautiful and profound results in modern physics. It means that the very shape and consistency of the laws of nature depend on these delicate mathematical balances that keep certain particles forever massless. However, not all particles that appear massless in theory are truly so. For example, neutrinos were once thought to be completely massless like photons, but experiments have shown that they have a tiny but non-zero mass. Because of this, they can travel very close to light speed but not exactly at it. They are almost the exception, but not quite. The difference, though small, has huge consequences for how neutrinos behave across cosmic distances and how they interact with matter. It also helps scientists understand why the universe contains more matter than antimatter, a mystery that still challenges physicists today. The idea of a truly massless particle challenges human understanding because everything we touch, see, or experience in everyday life has mass. We're used to things that stop when we push them, that take time to speed up, that resist motion. A photon does none of this. It cannot be stopped, stored, or slowed. It exists only as movement, only as an eternal rush across the fabric of space. Its entire being is defined by speed. This makes photons unique not just in physics, but also in the story of the cosmos. Every star in the night sky sends out countless photons into space, each one travelling endlessly until it strikes an eye, a telescope, or a distant world. The light from the sun takes about 8 minutes to reach Earth, crossing nearly 150 million kilometers of empty space. The light from the nearest star takes more than 4 years to arrive. Some of the light that reaches us tonight from distant galaxies began its journey more than 13 billion years ago, when the universe itself was young. These ancient photons carry with them the story of creation, travelling unaltered since the dawn of time. Yet, even though they are ancient and massless, photons remain energetic and vital. They heat planets, drive photosynthesis in plants, and power the entire web of life on Earth. They bring energy from stars to worlds, allowing chemical reactions to happen and ecosystems to thrive. Every colour we see, every shadow we notice, and every sunrise we admire is the result of massless particles touching our eyes and activating the cells that let us perceive light. Without them, there would be no sight, no warmth, and perhaps no life at all. The study of massless particles continues to guide modern science. In laboratories and observatories around the world, scientists study light in all its forms: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Each of these is a form of electromagnetic radiation, made of photons with different energies but the same speed. From studying the faint microwave glow left over from the Big Bang to observing the brilliant gamma rays from exploding stars, We are constantly learning how these particles reveal the secrets of the cosmos. The same principles apply to gravitational waves, ripples in spacetime that travel at light speed. If gravitons exist, they too would be massless, and their movement would mirror that of photons, though they would carry the information of gravity rather than light. In 2015, scientists detected gravitational waves directly for the first time, confirming a prediction made by Einstein a century earlier. This discovery opened a new window on the universe, showing that the laws of relativity and the behavior of massless phenomena extend even to the most massive and violent events in existence. The more physicists learn about massless particles, the more they understand how tightly woven the universe truly is. Every force, every interaction, every ray of light that reaches across the void depends on these tiny messengers that have no mass but limitless speed. They do not age, they do not rest, and they do not change their pace. They are the pure expression of motion itself, the embodiment of energy without weight. Photons and other massless particles stand apart from everything else in the universe. They are not bound by the same restrictions that hold stars, planets, or people in place. They are the silent threads that connect the cosmos, racing through the emptiness between galaxies, carrying the stories of the past to the present. They show that not everything in existence needs mass to have meaning, and that sometimes the most powerful things are those that move forever, unburdened by anything except the laws of the universe that set them free at the speed of light. The universe, in all its vastness and mystery, is not just an endless emptiness where planets, stars, and galaxies float like scattered dust. Beneath everything we see and experience lies an invisible but powerful fabric called spacetime. This fabric is not a thing we can touch or hold in our hands, yet it defines every movement, every orbit, every ray of light, and even the way time itself passes. To understand why light speed stands as the absolute limit, and why the geometry of the universe itself sets boundaries on motion, we must dive into the deep and fascinating relationship between light, gravity, and the hidden curves of space and time. Long ago, people believed that space and time were two completely separate things. Space was simply the stage where everything happened, while time was like an endless ticking clock that moved forward the same way everywhere in the universe. But in the early 20th century, Albert Einstein shattered this idea when he proposed that space and time are actually one single, united thing, space-time. He showed that the universe behaves not like a rigid frame, but like a flexible, bendable fabric that can be stretched, twisted, and curved by the presence of matter and energy. Every planet, star, and black hole shapes this fabric, and that shape controls how objects move and how light travels. When we say that space-time is curved, we do not mean it bends like a physical sheet of paper, but rather that the very geometry of reality itself changes depending on what is nearby. In a region where there is no mass or energy, space-time is flat, and light travels in straight lines at the constant speed of nearly 300,000 kilometers per second. But near a massive object such as a star or a planet, space-time curves and light follows that curve. It still travels at the same speed locally, but the path it takes is no longer straight, it bends. That bending of light around massive objects is what we call gravitational lensing, and it is one of the strongest pieces of evidence that space-time really does curve. The fact that light always moves at the same speed no matter how one is moving, or where one is in the universe, is one of the most extraordinary discoveries in science. It was this constant speed that led Einstein to realize that space and time must stretch and compress, depending on how fast one moves. The faster something moves through space, the slower time passes for it, and the shorter distances appear in the direction of its motion. This balance keeps the speed of light constant and unbreakable. It is not simply a rule of nature, but a result of the very structure of space-time. The geometry of the universe is built in such a way that nothing with mass can reach or exceed the speed of light, because doing so would require the geometry itself to be rewritten. In simple terms, the universe does not allow faster-than-light motion, because space and time would have to twist in impossible ways to make it happen. For an object with mass to approach light speed, its energy grows without limit. The closer it gets, the heavier it effectively becomes, and the more energy it takes to accelerate even a little bit more. To reach the speed of light would require infinite energy, and infinite energy does not exist in our physical reality. The geometry of space-time ensures that no amount of power, no technology, no clever trick can push a massive object past this cosmic boundary. The light speed limit is woven into the mathematical structure of the universe itself. But the story does not end there, because while spacetime sets limits, it also allows for some fascinating theoretical possibilities. Since spacetime can bend, stretch, and twist, physicists have long wondered whether it might also be possible to fold it in a way that brings two distant points close together. Imagine two locations in the universe that are separated by billions of light years. Even light, travelling at its incredible speed, would take billions of years to cross the distance between them. But if spacetime could somehow be bent so that these 2 points touch, one could, in theory, move from one to the other instantly, without ever exceeding the speed of light. This is the basic idea behind a wormhole. A wormhole is a hypothetical tunnel or bridge through the fabric of spacetime. The term was first used in the 20th century, though the concept has roots in Einstein's equations themselves. In 1915, Einstein published his general theory of relativity, which described how matter and energy curve spacetime. Shortly after, in 1916, a German physicist named Karl Schwarzschild found a solution to Einstein's equations that described the gravitational field around a spherical mass. This solution later helped define what we now call a black hole. In the years that followed, other scientists studied the equations further and discovered that under certain conditions, it might be possible to connect two separate points in spacetime through a tunnel-like structure. Such a structure would be extremely strange. One mouth of the wormhole could be located near Earth, while the other could open somewhere far across the galaxy, or even in another universe, if such universes exist. If someone could enter one side and come out the other, it would effectively be a shortcut through the fabric of reality. Travelling through a wormhole would not mean moving faster than light in the usual sense, because the traveller would not be crossing normal space. Instead, space itself would be folded to shorten the journey. However, this idea raises enormous challenges. According to what we know from Einstein's equations, a wormhole would not be stable under normal conditions. It would collapse almost instantly after forming, closing before anything could pass through it. The reason lies once again in the structure of space-time. The gravitational forces inside such a tunnel would be unimaginably strong, pulling the walls together and sealing the passage. To keep a wormhole open, one would need a form of matter with very unusual properties, something with negative energy or negative mass, which we have never observed in nature. This hypothetical substance is often called exotic matter. Exotic matter is not the same as dark matter, which scientists believe makes up much of the universe's hidden mass. Exotic matter would behave in a completely different way. Instead of being pulled by gravity, it would push against it. In theory, this repulsive effect could balance the forces that try to close a wormhole, keeping it open long enough for something, or someone, to pass through. The concept sounds like pure science fiction, yet it appears again and again in the mathematics of general relativity and in the imaginations of physicists who explore the universe's most extreme possibilities. If such wormholes could exist and remain stable, they could, in theory, allow not only faster travel across vast distances, but also strange effects involving time. Because space and time are connected, bending space also means bending time. Some calculations suggest that a wormhole could act as a kind of time machine, linking 2 points that are not only separated in space but also in time. Travelling through it could allow one to move into the past or the future, depending on how the ends of the wormhole are arranged and how they move relative to each other. The idea of time travel through wormholes has fascinated scientists and storytellers alike. Physicists like Kip Thorne and Carl Sagan popularised the concept in the late 20th century, showing how general relativity does not entirely forbid it, though it demands conditions far beyond anything humanity could currently achieve. The energy required to create or stabilise a wormhole would be enormous, possibly equal to the total energy output of a star. Moreover, even if one could somehow build such a structure, it might be destroyed by quantum effects. Tiny fluctuations in energy, predicted by quantum field theory, could destabilise the tunnel, causing it to collapse violently. Despite all these difficulties, the concept of wormholes continues to capture the imagination because it touches on the deepest mysteries of the universe. It connects the cosmic speed limit, the geometry of space-time, and the possibility that the universe might allow shortcuts through its structure. In some theories, wormholes might even occur naturally. For instance, in the chaotic first moments after the Big Bang, space-time could have been filled with rapid fluctuations, stretching and folding in every direction. Some physicists think that tiny wormholes might have formed during that time. These would be unimaginably small, far smaller than atoms, and they might have existed only for a fraction of a second before disappearing. Yet if even one such wormhole had survived, it could still be hidden somewhere in the universe waiting to be discovered. In recent decades, researchers have also explored the connection between wormholes and another deep concept: quantum entanglement. Entanglement is a strange feature of quantum mechanics in which two particles can remain connected across any distance. If one particle is measured, the other instantly reacts, even if it is light years away. Some scientists, including Juan Maldacena and Leonard Susskind, have proposed that entangled particles might be linked by tiny quantum-scale wormholes. This idea, sometimes called the ER-EPR conjecture, suggests that wormholes and quantum entanglement could actually be two sides of the same coin. The letters ER refer to Einstein and Rosen, who described an early wormhole model called the Einstein-Rosen bridge, while EPR refers to a famous paper by Einstein, Podolsky and Rosen about quantum entanglement. If this idea is true, it could mean that space-time itself emerges from patterns of quantum entanglement. In other words, the very fabric of the universe might be woven together by invisible threads connecting quantum particles. In this view, light speed would still remain the limit for motion through space, but the deep structure of the universe could include hidden connections that make distances and separations less absolute than they appear. The geometry of space-time, then, would not just constrain movement, it would be the very result of the underlying quantum relationships between all things. Einstein's equations describe how matter tells space-time how to curve, and how space-time tells matter how to move. This elegant relationship means that nothing moves freely through space without being guided by the shape of the universe itself. Even light, which has no mass, follows these curves perfectly. That is why starlight bends around galaxies, why black holes trap light in orbits, and why even the most advanced spacecraft can never go faster than that constant cosmic pace. Near a black hole, space-time curves so sharply that not even light can escape once it passes a certain boundary called the event horizon. Inside this region, all paths through space-time lead inward. The geometry becomes so extreme that time and space trade places. Moving forward in time becomes the same as moving deeper into the black hole. If one could somehow survive the fall, the equation suggests that the center might lead to another region of space-time altogether. This theoretical point is sometimes called a singularity, a place where the known laws of physics break down completely. Some physicists speculate that wormholes might form at such singularities, linking different regions of the universe, or even different universes. But if wormholes exist inside black holes, they would be hidden from us by the event horizon, making them impossible to reach or observe directly. Still, the mathematics remains consistent with the idea that space-time could be far more complex and connected than we can see. Every galaxy, every black hole, every ripple in space might contribute to a vast cosmic network of invisible pathways, even if most are closed or unstable. The geometry of space-time is not fixed or static. It can ripple like a pond when disturbed by massive objects moving through it. These ripples are called gravitational waves, and they were first predicted by Einstein in 1916. For a century they remained a mathematical idea, until in 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, known as LIGO, finally detected them for the first time. The waves came from two black holes merging more than 1 billion light-years away. As they spiraled together, their immense gravity distorted space-time, sending waves that eventually reached Earth. The detection confirmed that space-time is indeed a dynamic, flexible structure, not an empty void. These gravitational waves move at the speed of light, carrying information about the most violent events in the cosmos. Their discovery deepened our understanding of how the geometry of the universe responds to motion, energy, and change. It also reminded us that the light speed limit is not just a property of light itself, but of space-time as a whole. The waves that shake the universe travel at the same ultimate speed, reinforcing the idea that this constant is built into the very structure of reality. Scientists continue to study the geometry of space-time using telescopes, particle accelerators, and theoretical models. They look for hints of how gravity and quantum mechanics might fit together into a single theory. General relativity describes the large-scale structure of the cosmos: planets, stars, galaxies, and black holes, while quantum physics explains the tiny world of atoms and particles. But these two descriptions do not yet fit perfectly together. Somewhere, at the deepest level, space-time itself might be quantized, made of incredibly small units that combine to form the smooth geometry we experience. If that is true, then the cosmic speed limit and the shape of the universe might emerge naturally from the way these quantum units interact. Some physicists think of space-time as a kind of quantum fabric woven from information, where distances, times, and even gravity arise from microscopic patterns. In such a universe, wormholes might not just be science fiction, they could be part of the hidden structure linking quantum states together. But at our human scale, the effects of this deep structure remain invisible, and the speed of light remains the ultimate limit we can observe. The connection between light speed and space-time geometry goes beyond physics. It touches the very nature of reality. Every movement, every change, every cause and effect unfolds within this cosmic structure. Time does not flow separately from space. It is part of the same dynamic fabric. To move through space is also to move through time, and the faster one moves through space, the slower time passes in return. This perfect balance keeps everything in harmony, ensuring that nothing breaks the rules written into the geometry of the universe. Some researchers have proposed alternative ideas for how to travel vast cosmic distances without breaking the light speed barrier. One such idea is the warp drive, inspired by theoretical work by physicist Miguel Alcubierre in the 1990s. The Alcubierre drive would not accelerate a spaceship through space faster than light. Instead, it would create a bubble of space-time that contracts in front of the ship and expands behind it. Inside the bubble, the ship would remain still relative to its local space, while the bubble itself moves faster than light relative to distant observers. This would allow the ship to travel great distances without technically violating the cosmic speed limit. However, such a device would require enormous amounts of energy, possibly negative energy, to create and sustain the bubble. The mathematics suggests it might be possible, but the physics remains far beyond our reach. Once again, the challenge is the same. Manipulating the geometry of space-time requires conditions that are far beyond anything humanity can produce. The light speed limit is so deeply built into the structure of the universe that to bypass it would mean reshaping that structure itself. The relationship between light, space, and time is not just a scientific curiosity. It is the foundation of everything we experience. Every second that passes, every step we take, every ray of sunlight that warms the Earth, all follow the same geometric laws. The universe is like an enormous web where time and space stretch together, and light marks the tightest thread in that web, defining what is possible and what is not. Even when we look up at the night sky, we are not just seeing stars as they are, but as they were, because light takes time to travel. We are always looking back through the structure of space-time itself, witnessing history frozen in its glow. In distant galaxies, light that began its journey billions of years ago still follows the same unbreakable rule, crossing curved paths and expanding horizons. The universe stretches as it grows older, and as it does, space-time itself expands, carrying galaxies apart while light continues to move through it at its constant pace. The geometry changes, but the rule does not. The constant speed of light remains the anchor that holds together the vast cosmic fabric. This connection between speed, geometry, and the universe's structure shows how deeply light is woven into reality. Every law of physics, every event, and every possibility follows the geometry of space-time, which itself shapes what motion, distance, and time can mean. Wormholes, warp drives, and all other cosmic dreams are attempts to explore or bend that geometry, to find hidden pathways through the folds of creation. Yet even these ideas, wild as they are, still obey the same fundamental rule, that nothing in normal space can move faster than light. Across the vast, cold darkness of the universe, human imagination has always reached beyond the stars. From the earliest stories told around fires to the grandest visions of modern science fiction, people have dreamed of travelling beyond the boundaries of the solar system, journeying to distant suns, exploring strange new worlds, and perhaps finding life among the stars. Yet between humanity and those faraway realms lies a barrier that is not made of matter or energy, but of nature's own design, the ultimate speed limit, the speed of light. It is this limit that defines what is possible in the cosmos, and what remains, at least for now, only within the realm of dreams. The speed of light, about 300,000 kilometers every second, is the fastest any form of information, energy or matter can travel through space. This might sound unimaginably fast, but when one considers the enormous distances between stars, even this incredible speed becomes frustratingly slow. Light from the nearest star to Earth, Proxima Centauri, takes more than 4 years to reach us. That means if a spacecraft were to travel at the same speed as light, it would still take over 4 years to reach the closest stellar neighbour. The problem becomes even more daunting when one considers other stars that lie tens, hundreds, or thousands of light years away. Travelling to those distant regions of the galaxy would take entire human lifetimes, or even many generations, if one were limited by the laws of physics as we currently understand them. Because of this, scientists and engineers have long wondered whether there might be a way to break this cosmic speed limit. Could there exist some loophole in the universe that would allow travellers to move faster than light without violating the fundamental laws of physics? Theoretical concepts like wormholes, warp drives, and tachyons have all been explored as possible solutions, but none have yet proven to be practical or even physically possible. For now, the speed of light remains the absolute boundary between what can be done and what can only be imagined. The light speed barrier creates enormous challenges for interstellar travel. If a spacecraft were to move close to the speed of light, strange effects predicted by Einstein's theory of relativity would begin to occur. Time would slow down for the travellers aboard the ship, distances would appear shorter in the direction of motion, and mass would effectively increase as the ship's velocity climbed. These effects, while fascinating, also make it clear why reaching light speed itself is impossible for any object that has mass. As a spacecraft accelerates closer and closer to that limit, the amount of energy required to continue speeding up grows without bound. To actually reach light speed would require infinite energy, something no technology could ever provide. Even travelling at a fraction of light speed presents enormous technical challenges. Let us imagine a ship capable of reaching just 1/10 of the speed of light, or about 30,000 kilometers per second. That is still far beyond anything humanity has ever achieved. The fastest spacecraft ever launched by humans, such as the Parker Solar Probe, move at speeds of only a few hundred kilometers per second. Reaching 1/10 of light speed would require not only vast amounts of energy, but also materials strong enough to withstand unimaginable stresses. A single grain of dust encountered at that speed could hit the ship with the force of a bomb. The vacuum of space is not completely empty, and collisions with even tiny particles could cause catastrophic damage. The issue of energy alone is enough to make near-light speed travel an almost impossible task with current or foreseeable technology. To accelerate a spacecraft to a significant fraction of light speed, one would need to supply enormous amounts of energy, far greater than all the energy humanity currently produces in an entire year. The rocket equation, which governs how much fuel is required to reach a certain velocity, becomes especially punishing at such high speeds. Each kilogram of propellant adds to the total mass that must itself be accelerated, creating a vicious cycle of energy demand. Traditional chemical rockets would be useless for such journeys. Even nuclear propulsion, whether fission or fusion, might not provide enough thrust or efficiency to bring a large ship to near-light velocities. Some physicists have imagined more exotic forms of propulsion. Concepts like matter-antimatter engines, light sails pushed by powerful lasers, or fusion drives fueled by hydrogen gathered from interstellar space have all been suggested. These ideas could, in theory, push a spacecraft to speeds that are a respectable fraction of light speed, perhaps 1/10 or even 1/5. Yet even these methods face severe engineering challenges. For example, storing and using antimatter safely would be extraordinarily difficult, as any contact with normal matter would cause it to annihilate instantly, releasing tremendous energy. Similarly, building a laser powerful enough to propel a large spacecraft would require technological capabilities far beyond our present reach. Even if such propulsion systems could be built, another challenge arises: how to slow down once the ship reaches its destination. Travelling at high fractions of light speed means carrying not only the energy to accelerate, but also the energy to decelerate upon arrival. Without a way to stop, a ship would simply race past its target star and continue endlessly into the void. That means any interstellar mission would require careful planning, efficient propulsion, and possibly even new physics to make such travel feasible. The concept of near light speed travel also carries deep philosophical and emotional implications. Imagine a crew of explorers leaving Earth aboard a spacecraft travelling at 99% of light speed. To those aboard, time would seem to flow normally. They might experience only a few years on their journey, yet when they returned, centuries could have passed on Earth. This effect, known as time dilation, is one of the most mind-bending consequences of relativity. It means that interstellar travellers could, in a sense, journey into the future simply by moving fast enough. But this also means that they would leave behind everything and everyone they knew, returning to a world that has long moved on without them. For robotic probes, time dilation is not an emotional concern, but the practical difficulties remain immense. For humans, however, the psychological and social costs would be profound. A mission to another star, even at near light speed, could mean never returning to the same Earth. The society, language, and culture they left behind would have changed beyond recognition. In a way, each interstellar journey could be a one-way trip, not just across space but also across time. Because of these enormous obstacles, most current efforts in space exploration focus on robotic probes that move relatively slowly compared to light. Such missions can last decades, centuries, or even millennia, and while they might not carry humans, they can still gather valuable information. Probes like Voyager 1 and Voyager 2, launched in the late 20th century, are already travelling beyond the solar system. Although they move at only about 17 kilometers per second, tiny compared to light speed, they still represent humanity's first physical steps toward the stars. In millions of years, those small metal messengers will drift silently between the stars, carrying with them traces of human culture and curiosity. Many scientists now think that the most realistic path toward interstellar exploration will involve a combination of advanced robotics, artificial intelligence, and perhaps microscopic or nanoscopic spacecraft driven by light sails. The Breakthrough Starshot initiative, for example, envisions launching tiny probes attached to ultra-thin sails and pushing them with powerful ground-based lasers. If the technology could be made to work, such probes might reach speeds up to 20% of light speed. At that rate, they could reach the Alpha Centauri system in just over 20 years. That is still far slower than light itself, but it is a dramatic improvement over what current rockets can achieve. However, even these miniature missions face staggering challenges. The laser system would need to be immensely powerful and precisely focused, operating for minutes or hours to accelerate the probes. The tiny craft would need to survive the harsh environment of space, the bombardment of dust particles, and the intense radiation of nearby stars. Communicating across light years with such small devices would also be difficult, as their power supply and antennas would be minuscule. Yet the very fact that scientists are seriously considering such ideas shows how deeply humanity longs to reach beyond its home star. The limitations imposed by the speed of light also shape how we think about the structure of the universe itself. Because light takes time to travel, looking at distant stars and galaxies is like looking back in time. When astronomers observe a galaxy 10 billion light-years away, they are seeing it as it was 10 billion years ago. This means that even if humans someday travel at near-light speed, the universe will always keep its secrets hidden behind vast spans of time and distance. Each journey into the cosmos is also a journey into the past, a glimpse of what the universe once was long before our world even existed. From another perspective, the light speed limit might not be a curse, but a kind of cosmic safeguard. It prevents instantaneous communication and travel, ensuring that causality, the order of cause and effect, remains consistent throughout the universe. Without this rule, strange paradoxes could arise, such as messages being received before they are sent, or events influencing their own causes. The speed of light thus forms not just a barrier to travel, but a fundamental pillar of reality itself. It keeps the fabric of space and time stable and predictable, even if it frustrates our desire to explore. Still, human creativity refuses to be confined by such boundaries. In science fiction, authors and filmmakers often imagine ways to bypass the speed of light, inventing devices like warp drives or hyperspace engines that allow instant travel across the galaxy. These stories inspire real scientists to think boldly and ask whether such ideas might one day be more than fantasy. Theoretical physicists have proposed mechanisms like the Alcubierre drive, which involves contracting space in front of a spacecraft and expanding it behind. In principle, this would allow the ship to move faster than light relative to distant observers without locally breaking the laws of physics. Yet the amount of energy required for such a feat would be astronomical. perhaps more than the total mass energy of entire planets. Until such power can be controlled, such concepts remain far beyond our reach. Even if a practical form of near light-speed travel were developed, the journey between stars would still be incredibly lonely and perilous. Space is vast and mostly empty, filled with radiation, cosmic rays, and interstellar dust. Communication with Earth would become increasingly delayed as the ship moved farther away. At a distance of 1 light-year, messages would take 1 year to travel each way, making real-time communication impossible. The farther one went, the more isolated the travelers would become. They would have to rely entirely on their own systems, their own knowledge, and perhaps their own descendants to continue the mission. Such realities force us to rethink what interstellar travel might truly mean. Perhaps it will not involve giant ships carrying hundreds of people, but rather self-replicating robotic probes capable of spreading gradually from star to star over millennia. Or perhaps humans will choose to send their consciousness, encoded digitally, across the void instead of their physical bodies. Others imagine that our descendants may not be biological at all, but rather synthetic beings who do not age, tire, or require air, food, or water. For them, even 1,000-year journeys might be bearable. In another vision, near light-speed travel might be achieved not by brute force, but by clever use of physics. Scientists have speculated that future explorers could use gravitational slingshots around stars or black holes to gain tremendous speeds without expending as much fuel. By looping close to massive objects, a spacecraft could steal a bit of their momentum, much like current missions use planetary flybys to accelerate. If such maneuvers were combined with advanced propulsion, it might be possible to push a probe to significant fractions of light speed. Even if these techniques could bring the stars within reach, the psychological experience of travelling at near light speed would be unlike anything humanity has ever known. To those aboard the ship, time would seem to pass normally, but from the perspective of Earth, years or centuries could go by. A crew might set out knowing that by the time they arrived, everyone they knew would be gone and their homeworld changed beyond recognition. Communication would be delayed or lost entirely, and they would have to adapt to life as pioneers in a cosmos that stretches endlessly ahead of them. This time distortion also introduces a strange paradox for exploration. For the travellers, a journey of tens of light years might feel like only a few years, due to time dilation. But the civilization that sent them would have changed so much that there would be no one left to welcome them back. In this way, near light-speed travel offers not just a technological challenge, but a profound emotional and philosophical one. Each voyage to the stars would separate humanity from its past and its roots, transforming travellers into citizens of a new and distant future.